Imagine a place in the universe where not one, not two, but 13 stars are locked in a cosmic dance, swirling around each other in a chaotic yet mesmerizing ballet. This isn't science fiction, it's the reality of Tredecuple star systems, one of the most bizarre and mysterious phenomena in the cosmos. These systems, with their intricate gravitational webs and extreme conditions, challenge everything we think we know about how stars and planets form, survive, and interact. And today, we're diving deep into 50 of the strangest discoveries ever made about these mind-bending star systems. From unstable orbits that defy prediction to the possibility of alien life thriving in the most hostile environments, each discovery will leave you questioning what else the universe is hiding. So, if you're ready to explore the unknown and uncover secrets that even scientists are still trying to unravel, stay with us. By the end of this video, you'll see the night sky in a whole new light, and you might just wonder if we're truly alone in this vast, star-filled expanse. Let's begin. Now, let's take a closer look at the very first Tredecuple star system ever discovered. This groundbreaking find occurred in the constellation of Orion, a region of the night sky already famous for its dazzling stars and cosmic wonders. Astronomers first detected this system using advanced telescopes equipped with high-resolution imaging and spectroscopy, which allowed them to identify not just one or two stars, but a staggering 13 stars all gravitationally bound together. What made this discovery so extraordinary was the sheer complexity of the system. Unlike binary or triple star systems, which are relatively common, a Tredecuple system represents a level of cosmic chaos that challenges our understanding of stellar formation and dynamics. The stars in this system are arranged in a delicate balance, with some orbiting each other closely while others are flung into wide, looping paths. This discovery not only expanded our knowledge of star systems, but also opened up new questions about how such intricate configurations can exist in the first place. It's a reminder that the universe is far stranger and more unpredictable than we could ever imagine. And this was just the beginning. Each of the 50 discoveries we'll explore today builds on this foundation, revealing even more about the mysteries of Tredecuple star systems. Now, shifting our focus to the chaotic dance of stars within Tredecuple systems, we uncover a fascinating phenomenon: unstable orbits. Unlike the predictable paths of planets in our solar system, the stars in these complex systems are locked in a gravitational tug-of-war that defies simplicity. With 13 stars pulling on one another, the gravitational interactions become a cosmic game of push and pull, leading to orbits that are anything but stable. Some stars may spiral inward, drawn by the immense gravity of their neighbors, while others are flung outward into wide, erratic paths. This constant gravitational jostling creates a dynamic environment where orbits can shift dramatically over time, sometimes even leading to stars being ejected from the system entirely. The unpredictability of these movements challenges our understanding of celestial mechanics and raises intriguing questions about the long-term survival of such systems. What's even more astonishing is that these chaotic orbits can produce rare cosmic events, like close encounters between stars that result in spectacular flares or even collisions. This instability isn't just a quirk of Tredecuple systems. It's a window into the raw, untamed forces that shape the universe. And as we'll see in the next discovery, these gravitational interactions also give rise to some of the most extreme and unusual star types ever observed. Now, let's turn our attention to one of the most captivating aspects of Tredecuple star systems: the presence of rare and extraordinary star types. Among the 13 stars in these systems, astronomers have discovered some of the most unusual and extreme stellar objects in the universe. Take hypergiants, for example. These are among the largest and most luminous stars known, with sizes that can dwarf our own sun by hundreds of times. In tredecuple systems, hypergiants often dominate their surroundings, casting intense radiation across vast distances and influencing the behavior of neighboring stars. But their sheer size comes at a cost. Hypergiants burn through their fuel at an astonishing rate, leading to relatively short lifespans and dramatic ends, often culminating in supernovae that can reshape the entire system. Equally fascinating are neutron stars, the dense remnants of massive stars that have exploded and collapsed. In tredecuple systems, neutron stars add another layer of complexity to the gravitational dynamics. These incredibly dense objects, often no larger than a city, pack the mass of an entire star into a tiny volume. Their intense gravitational pull can warp the orbits of nearby stars, creating even more instability in an already chaotic environment. Some neutron stars in these systems are also observed as pulsars, emitting beams of radiation that sweep across space like cosmic lighthouses. These pulsars provide valuable clues about the magnetic fields and rotational speeds of these exotic objects, offering scientists a unique window into the physics of extreme stellar remnants. The presence of such rare star types in tredecuple systems isn't just a cosmic curiosity, it's a testament to the incredible diversity of stellar evolution. These systems act as natural laboratories where the interplay of multiple stars creates conditions that are rarely seen elsewhere in the universe. From hypergiants to neutron stars, each rare star type contributes to the intricate tapestry of these systems, revealing new insights into how stars form, evolve, and ultimately meet their fates. And as we'll see in the next discovery, the extreme gravitational forces at play in these systems take this complexity to an entirely new level. Now, let's dive into the gravitational chaos that defines tredecuple star systems. Unlike binary or triple star systems, where the gravitational interactions are relatively straightforward, tredecuple systems are a cosmic whirlwind of forces. With 13 stars orbiting one another, the gravitational pull becomes a tangled web of influences, creating an environment where stability is rare and unpredictability reigns supreme. Each star exerts its own gravitational force, pulling on the others in a constant tug of war. This results in orbits that are anything but smooth. Stars can be flung into wildly elliptical paths or even ejected from the system entirely, leaving behind a trail of gravitational ripples. The sheer number of stars in these systems amplifies the complexity. In a binary system, two stars orbit a common center of mass, and their gravitational dance is relatively predictable. Add a third star and things get more complicated but still manageable. But in a tredecuple system, the gravitational interactions become so intricate that even the most advanced simulations struggle to predict their long-term behavior. Stars can pass dangerously close to one another, creating intense gravitational tides that distort their shapes and trigger bursts of energy. These close encounters can also lead to dramatic events, such as stars being torn apart or merging into larger, more massive objects. The impact of these extreme gravitational forces extends far beyond the stars themselves. Surrounding space is shaped by the relentless pull of these massive objects. Dust clouds, gas, and even potential planets are subjected to constant gravitational stress, making it nearly impossible for stable structures to form. Any planets that do manage to exist in such a system would face a harsh reality: extreme temperature fluctuations, erratic orbits, and the constant threat of being flung into the void or consumed by a nearby star. The gravitational forces in tredecuple systems are so intense that they can even bend light, creating bizarre visual effects like gravitational lensing, where the light from distant stars is warped and magnified as it passes through the system. What makes these gravitational forces so fascinating is their ability to reveal the hidden dynamics of the universe. By studying how stars interact in tredecuple systems, scientists gain insights into the fundamental laws of gravity and the behavior of matter under extreme conditions. These systems are like cosmic laboratories, offering a glimpse into the chaotic processes that shape the universe on a grand scale. And as we'll see in the next discovery, this gravitational chaos doesn't just affect the stars, it also gives rise to some of the most mysterious signals ever detected in space. Now, let's turn our attention to one of the most puzzling phenomena in Tredecuple star systems: mysterious radio signals. These signals, detected by astronomers, have sparked both curiosity and debate within the scientific community. Unlike the predictable radio waves emitted by stars or other celestial objects, these signals are erratic, intense, and seemingly without a clear origin. What makes them even more intriguing is that they appear to originate specifically from Tredecuple systems, adding another layer of mystery to these already chaotic cosmic environments. One leading theory suggests that these radio signals could be the result of extreme gravitational interactions between the stars. As stars in Tredecuple systems pass close to one another, their intense gravitational forces might generate powerful magnetic fields. These fields, in turn, could accelerate charged particles to near light speeds, producing bursts of radio waves. Another possibility is that these signals are linked to the presence of black holes within the system. If a black hole is feeding on surrounding matter, it could emit jets of energy that manifest as radio signals detectable from Earth, but there's more to the mystery. Some scientists speculate that these signals could be evidence of advanced alien civilizations. While this idea remains highly speculative, it's not entirely out of the question. The complex dynamics of Tredecuple systems might create conditions that could support life, albeit under extreme circumstances. If such life exists, it's possible that they've developed technology capable of producing these signals. However, without concrete evidence, this theory remains in the realm of fascinating speculation. What's certain is that these mysterious radio signals offer a unique window into the inner workings of Tredecuple systems. By studying them, astronomers hope to uncover clues about the behavior of matter and energy under extreme conditions. Each signal detected is like a piece of a cosmic puzzle, helping us better understand the forces that shape these complex star systems. And as we'll see in the next discovery, the chaos within Tredecuple systems doesn't stop at radio signals. It also leads to some of the most spectacular stellar collisions in the universe. Now, let's dive into one of the most dramatic events that can occur in Tredecuple star system: star collisions. With so many stars packed into a relatively small space, the likelihood of collisions is significantly higher compared to simpler star systems. These cosmic crashes are not just rare occurrences, they are some of the most energetic and awe-inspiring events in the universe. When two stars collide in a Tredecuple system, the result is nothing short of spectacular. The immense gravitational forces at play can trigger a series of explosive events, such as supernova or gamma-ray bursts. A supernova occurs when a star reaches the end of its life and explodes, releasing an incredible amount of energy and light. In Tredecuple systems, the collision of two stars can accelerate this process, leading to supernovae that outshine entire galaxies for a brief moment. Gamma-ray bursts, on the other hand, are even more extreme. These are the most energetic explosions in the universe, often lasting just a few seconds but releasing more energy than our Sun will emit in its entire lifetime. When stars collide in Tredecuple systems, the resulting gamma-ray bursts can be detected across vast cosmic distances, providing astronomers with valuable data about the conditions that lead to such powerful events. But what makes these collisions even more fascinating is their aftermath. The debris from a star collision can form new stars, planets, or even black holes, creating a cycle of cosmic rebirth. This process not only reshapes the Tredecuple system, but also contributes to the evolution of the surrounding region of space. The remnants of these collisions can also produce exotic objects, such as neutron stars or magnetars, which have incredibly strong magnetic fields and spin at astonishing speeds. The study of star collisions in Tredecuple systems offers a unique opportunity to understand the life cycle of stars and the forces that drive cosmic evolution. Each collision is a natural laboratory, allowing scientists to observe the behavior of matter and energy under the most extreme conditions. And as we'll see in the next discovery, the chaos of Tredecuple systems doesn't end with collisions. It also gives rise to some of the most unusual planetary systems ever observed. Now, shifting our gaze from the explosive chaos of star collisions, let's turn our attention to something equally intriguing: the possibility of planets existing within Tredecuple star systems. At first glance, the idea of planets forming and surviving in such a crowded and volatile environment seems almost impossible. Yet, nature has a way of surprising us, and Tredecuple systems are no exception. In these complex systems, planets face a host of extreme challenges. The gravitational pull from multiple stars creates a chaotic environment, making stable orbits incredibly rare. Imagine a planet being tugged in different directions by 13 stars, each exerting its own gravitational force. This constant tug of war can lead to wildly erratic orbits, making it difficult for planets to maintain a consistent path around any one star. Some planets might even be flung out of the system entirely, becoming rogue planets drifting through the void of space. But despite these challenges, astronomers have theorized that planets could still form and persist in Tredecuple systems. One possibility is that planets might orbit a single star within the system, staying far enough away from the gravitational influence of the other stars. These planets would need to be in a delicate balance, carefully navigating the gravitational minefield to avoid being destabilized. Another scenario involves planets orbiting multiple stars in a wide, stable configuration, similar to how some planets in binary or triple star systems manage to survive. The conditions on these planets would be unlike anything we've seen in our own solar system. With multiple stars in the sky, the concept of day and night would be far more complex. A planet might experience multiple sunrises and sunsets in a single day, or it could be bathed in perpetual twilight if it orbits far enough from its primary star. The temperature variations would also be extreme, with the planet's surface heating and cooling rapidly as it moves between the gravitational influences of different stars. And then there's the question of habitability. Could life exist on a planet in a Tredecuple system? The odds are slim, but not impossible. The constant gravitational stress and extreme environmental conditions would make it a harsh place for life as we know it. However, if life did manage to take hold, it would likely be incredibly resilient, adapted to survive in one of the most hostile environments in the universe. The study of planets in Tredecuple systems opens up a fascinating new frontier in astronomy. It challenges our understanding of how planets form and evolve, and it pushes the boundaries of what we consider possible in the cosmos. As we continue to explore these strange and complex systems, who knows what other surprises might be waiting for us? And speaking of surprises, our next discovery takes us even deeper into the mysteries of Tredecuple systems, where black holes lurk, shaping the very fabric of these cosmic wonders. Now, as we venture further into the enigmatic realm of Tredecuple star systems, we encounter one of the most mysterious and powerful forces in the universe: black holes. These cosmic behemoths, known for their immense gravitational pull, play a pivotal role in shaping the dynamics of Tredecuple systems, adding yet another layer of complexity to these already intricate stellar arrangements. In Tredecuple systems, the presence of a black hole can dramatically alter the behavior of the surrounding stars. Imagine a black hole as the ultimate gravitational anchor, exerting an overwhelming influence on everything in its vicinity. Stars that stray too close to a black hole can be torn apart in a process known as spaghettification, where the intense tidal forces stretch and distort the star into long, thin streams of gas. Even stars that remain at a safe distance are not immune to the black hole's influence, as their orbits can be warped and destabilized, leading to chaotic and unpredictable movements. But black holes in tredecuple systems don't just act as destructive forces, they can also be catalysts for extraordinary cosmic events. For instance, the accretion disks that form around black holes, made up of gas and dust spiraling inward, can emit tremendous amounts of energy, lighting up the surrounding space with intense radiation. These glowing disks can outshine entire galaxies, making them some of the brightest objects in the universe. In tredecuple systems, the presence of multiple stars can feed these accretion disks, creating a dazzling display of cosmic fireworks. The gravitational interactions between a black hole and the stars in a tredecuple system can also lead to fascinating phenomena such as gravitational waves. When stars or black holes orbit each other at high speeds, they create ripples in the fabric of space-time which propagate outward as gravitational waves. These waves, first detected in 2015, provide astronomers with a new way to observe and study the universe. In tredecuple systems, the complex dance of stars and black holes could produce a symphony of gravitational waves, offering valuable insights into the nature of these systems. Moreover, black holes in tredecuple systems can serve as cosmic laboratories, allowing scientists to test theories about gravity, space-time, and the behavior of matter under extreme conditions. The intense gravitational fields near a black hole can cause time dilation, where time appears to slow down relative to an outside observer. This effect, predicted by Einstein's theory of general relativity, has been observed in other contexts, but tredecuple systems provide a unique environment to study it further. The presence of black holes also raises intriguing questions about the formation and evolution of tredecuple systems. Did the black hole form first, with the stars gathering around it, or did it emerge later, perhaps from the collapse of a massive star within the system? Understanding the origins of these black holes could shed light on the history of tredecuple systems and their place in the broader cosmos. As we continue to explore the mysteries of tredecuple star systems, the role of black holes stands out as a key area of interest. These enigmatic objects not only shape the dynamics of their surroundings but also challenge our understanding of the universe. And as we move forward, our next discovery takes us into the heart of star formation, where the birth of new stars in these complex systems reveals even more about the wonders of the cosmos. Now, shifting our gaze to the very beginnings of these cosmic wonders, let's dive into the fascinating processes of star formation within tredecuple systems. Unlike the relatively straightforward star formation we see in simpler systems, such as binary or single-star arrangements, the birth of stars in tredecuple systems is a chaotic and intricate dance of gravity, gas, and cosmic forces. In simpler systems, star formation typically begins within vast clouds of gas and dust, where pockets of material collapse under their own gravity, eventually igniting to form new stars. However, in tredecuple systems, the presence of multiple stars adds layers of complexity to this process. The gravitational pull of so many stars creates a turbulent environment, where gas and dust are constantly being pulled, pushed, and reshaped. This turbulence can either hinder or accelerate star formation, depending on the dynamics of the system. One of the most striking differences is the sheer scale of gravitational interactions. In a tredecuple system, the gravitational forces from multiple stars can compress gas clouds more intensely than in simpler systems, leading to the formation of more massive stars. These massive stars, in turn, can influence the surrounding environment, triggering further star formation in a chain reaction. It's like a cosmic domino effect, where the birth of one star sets off the creation of others nearby. Another unique aspect of star formation in tredecuple systems is the role of stellar winds and radiation. As stars form, they emit powerful winds and intense radiation that can sweep away surrounding gas and dust, potentially stifling the formation of new stars. However, in the crowded environment of a tredecuple system, These winds and radiation can also collide and interact, creating shock waves that compress nearby gas clouds and spark new rounds of star formation. It's a delicate balance between destruction and creation, where the very forces that could prevent star birth can also ignite it. The timing of star formation in these systems is also a key factor. In simpler systems, stars often form in relatively isolated pockets, leading to a more staggered timeline. But in Tredecuple systems, the close proximity of multiple stars means that star formation can occur in bursts, with entire clusters of stars being born simultaneously. This synchronized star birth can lead to the creation of tightly bound star groups, which may eventually evolve into smaller subsystems within the larger Tredecuple arrangement. Interestingly, the presence of older stars in Tredecuple systems can also play a role in shaping the formation of new ones. As older stars evolve and shed their outer layers, they enrich the surrounding gas with heavier elements, providing the raw materials needed for the next generation of stars. This recycling of stellar material ensures that star formation in Tredecuple systems is not just a one-time event but an ongoing process that can span millions or even billions of years. As we explore these star formation processes, it becomes clear that Tredecuple systems are not just static collections of stars but dynamic, ever-changing environments where the cycle of birth and rebirth plays out on a grand scale. And as we continue our journey, our next discovery takes us into the mesmerizing movements of these stars, revealing a cosmic dance that defies imagination. Now, let's step into the mesmerizing realm of motion, where the stars of Tredecuple systems perform an intricate ballet across the cosmos. Imagine a grand celestial stage where 13 stars whirl and twirl in a delicate yet chaotic dance, each movement dictated by the invisible threads of gravity. This is no ordinary waltz, it's a cosmic performance where every star plays a vital role, and the choreography is as unpredictable as it is breathtaking. In Tredecuple systems, the gravitational interactions between so many stars create a dynamic and ever-changing environment. Unlike simpler systems, where stars might follow relatively stable orbits, the stars here are constantly tugged and pulled by their neighbors, leading to a dance that is both beautiful and chaotic. Picture this: as one star moves, its gravitational influence ripples through the system, altering the paths of the others. This creates a chain reaction of motion where no two steps are ever the same. What makes this dance so fascinating is the sheer complexity of the movements. In a binary system, for example, two stars orbit a common center of gravity in a predictable pattern. But in a Tredecuple system, the gravitational forces are so intertwined that the stars can loop, spiral, and even swap places in their orbits. It's as if the stars are engaged in a cosmic game of musical chairs with gravity as the conductor. One of the most striking aspects of this dance is the way stars can form temporary partnerships. In the midst of their chaotic movements, two or more stars might come close enough to each other to form a binary or even a trinary subsystem within the larger Tredecuple arrangement. These partnerships can last for thousands or even millions of years before the stars are pulled apart by the gravitational influence of their neighbors, only to form new alliances later on. It's a dance of connection and separation where the stars are forever bound yet constantly changing partners. The speed of this dance is another marvel. In some Tredecuple systems, stars can orbit each other at incredible velocities, completing their paths in just a few years or even months. This rapid motion creates a dazzling display of light and energy as stars whip around each other, their surfaces glowing with the heat of their movement. At the same time, slower-moving stars add a sense of grace and elegance to the performance, creating a contrast that makes the dance all the more captivating. But this cosmic ballet isn't just a visual spectacle, it's also a window into the fundamental forces that shape the universe. By studying the movements of stars in Tredecuple systems, astronomers can gain insights into the nature of gravity, the behavior of matter under extreme conditions, and even the origins of the universe itself. Each twist and turn in the dance tells a story, revealing the intricate balance of forces that govern the cosmos. As we marvel at this celestial choreography, it's impossible not to feel a sense of awe at the sheer scale and complexity of the universe. The stars in Tredecuple systems remind us that even in the vastness of space, there is a delicate order to the chaos, a rhythm to the randomness, and as we continue our exploration, we'll uncover even more wonders, each one adding a new layer to our understanding of these extraordinary systems. Next, we'll turn our attention to the vast distances that separate these dancing stars and how they manage to stay connected across the void. Now, let's shift our gaze to the immense scales that define Tredecuple star systems. These systems aren't just complex in their movements, they're also vast beyond imagination. The distances between stars in a Tredecuple system can span light years, creating a cosmic tapestry where each star is a distant island in an ocean of space. Yet, despite these staggering distances, the stars remain bound together by the invisible threads of gravity, weaving a delicate web that defies the emptiness of the void. To put this into perspective, consider that a single light year is the distance light travels in 1 year, nearly 6 trillion miles. In Tredecuple systems, stars can be separated by multiple light years, meaning it would take light itself years to travel from one star to another. This raises a fascinating question. How do these stars maintain their gravitational bonds across such vast expanses? The answer lies in the sheer mass and gravitational pull of the system as a whole. Even though individual stars are far apart, their combined gravitational influence creates a unified field that keeps the entire system intact. One of the most intriguing aspects of these light-year spanning systems is how they challenge our understanding of gravity. In smaller systems like binaries or triples, the gravitational bonds are relatively straightforward, with stars orbiting close enough to exert a strong pull on one another. But in Tredecuple systems, the gravitational forces are distributed across enormous distances, creating a delicate balance that can be easily disrupted. This makes these systems incredibly dynamic, as even small changes in the positions or masses of the stars can ripple through the entire network, altering the gravitational landscape. Despite the vast distances, the stars in Tredecuple systems are far from isolated. They interact through gravitational waves, subtle ripples in spacetime that propagate across the system, carrying energy and momentum from one star to another. These waves act like cosmic messengers, ensuring that even the most distant stars remain connected. Over time, these interactions can lead to fascinating phenomena, such as stars being pulled closer together or pushed further apart, creating a constantly evolving dance of gravity. Another key factor in maintaining these gravitational bonds is the presence of intermediary stars. In a Tredecuple system, stars often form smaller subgroups, such as binaries or trinaries, which act as gravitational anchors. These subgroups help stabilize the larger system, creating a network of gravitational interactions that spans the entire structure. It's like a cosmic game of telephone, where the gravitational influence of one star is passed along through the system, ensuring that even the most distant stars remain part of the collective. The vast distances in Tredecuple systems also have profound implications for the way we observe them. From our vantage point on Earth, these systems often appear as a single point of light, with the individual stars too close together to resolve with even the most powerful telescopes. Yet, through careful analysis of their light and motion, astronomers can piece together the intricate structure of these systems, revealing the hidden dance of stars separated by light years. As we ponder the immense scales of Tredecuple systems, we're reminded of the incredible forces that shape the universe. These systems are a testament to the power of gravity, a force that can bridge the vast emptiness of space and bind stars together across unimaginable distances. And as we continue our journey through the mysteries of Tredecuple systems, we'll uncover even more wonders, each one revealing the delicate balance that holds the cosmos together. Next, we'll explore the presence of exotic matter within these systems and how it influences their behavior. Now, let's turn our attention to one of the most enigmatic aspects of Tredecuple star systems, the presence of exotic matter. These systems, with their intricate gravitational dances and vast scales, may also harbor forms of matter that defy our everyday understanding. Exotic matter, including dark matter, could play a crucial role in shaping the behavior and stability of these complex stellar arrangements. Exotic matter refers to substances that don't conform to the standard model of particle physics. Unlike ordinary matter, which makes up stars, planets, and everything we can see, exotic matter often interacts weakly with light and other forms of electromagnetic radiation. This makes it incredibly difficult to detect directly. However, its presence can be inferred through its gravitational effects, which can influence the motion of stars and other objects within a system. In Tredecuple star systems, the gravitational forces at play are already incredibly complex due to the sheer number of stars and their vast separations. The addition of exotic matter could introduce even more layers of complexity. For instance, dark matter, a form of exotic matter that doesn't emit or absorb light, could be distributed throughout the system, creating an invisible gravitational scaffold that helps hold the stars together. This unseen influence might explain why some Tredecuple systems remain stable despite the immense distances between their stars. One intriguing possibility is that exotic matter could act as a kind of cosmic glue, binding stars together in ways that ordinary matter alone cannot. In regions where dark matter is concentrated, its gravitational pull could counteract the disruptive forces that might otherwise tear a Tredecuple system apart. This could lead to the formation of stable, long-lasting systems that persist for billions of years, even as individual stars move and evolve. Another fascinating aspect of exotic matter in Tredecuple systems is its potential to influence the formation of stars and planets. If dark matter is present in significant quantities, it could affect the way gas and dust collapse to form new stars. This might result in unusual star types or planetary systems that wouldn't exist in simpler star systems. For example, the presence of dark matter could lead to the creation of stars with unusual compositions or orbits, adding yet another layer of mystery to these already complex systems. The effects of exotic matter aren't limited to gravity alone. Some theories suggest that certain types of exotic matter could generate unique electromagnetic fields or even interact with the fabric of spacetime itself. In Tredecuple systems, where the gravitational environment is already extreme, these interactions could produce phenomena that challenge our current understanding of physics. Imagine a star system where the very fabric of space is warped by the presence of exotic matter, creating conditions that are unlike anything we've observed before. Despite the challenges of detecting exotic matter directly, astronomers have developed ingenious methods to infer its presence. By studying the motion of stars within Tredecuple systems and comparing it to models that include or exclude exotic matter, researchers can gain insights into its distribution and effects. These studies not only shed light on the nature of Tredecuple systems, but also contribute to our broader understanding of the universe's hidden components. As we delve deeper into the mysteries of Tredecuple star systems, the role of exotic matter becomes increasingly significant. It's a reminder that the universe is filled with phenomena that lie beyond our current knowledge, waiting to be discovered. And as we continue to explore these systems, we may uncover clues that help us unravel the secrets of dark matter and other exotic substances, bringing us closer to understanding the true nature of the cosmos. Next, we'll examine how the intense gravitational fields in these systems can lead to another mind-bending phenomenon, time dilation. Now, shifting our gaze to another mind-bending aspect of Tredecuple star systems, we encounter a phenomenon that sounds like it's straight out of science fiction: time dilation. In these systems where the gravitational forces are unimaginably intense, time itself can behave in ways that defy our everyday experience. This is one of the most fascinating consequences of Einstein's theory of general relativity, and Tredecuple star systems provide the perfect cosmic laboratory to observe it. Time dilation occurs when the passage of time is affected by extreme gravitational fields. In simpler terms, time moves slower in regions where gravity is stronger. In a Tredecuple system, the combined gravitational pull of 13 stars creates an environment where this effect becomes significant. Imagine a star orbiting close to the center of such a system, where the gravitational forces are at their peak. For an observer on that star, time would appear to pass normally, but for someone watching from a distance, far from the system's intense gravity, time on that star would seem to slow down. This means that what feels like a single year for the star-bound observer could equate to decades or even centuries for the distant watcher. The implications of time dilation in Tredecuple systems are profound. For one, it could affect how we measure the ages of stars within these systems. A star experiencing strong gravitational time dilation might appear younger to an outside observer than it actually is. This could lead to discrepancies in our understanding of stellar evolution, as the observed lifetimes of stars might not align with theoretical predictions. Additionally, time dilation could influence the behavior of objects within the system, such as planets or even light itself. Light traveling through regions of intense gravity would be redshifted, meaning its wavelength would stretch and its energy would decrease. This could make certain parts of the system appear dimmer or redder than they actually are. Another intriguing possibility is how time dilation might impact the formation and stability of planets within Tredecuple systems. If a planet orbits a star in a region of strong gravitational time dilation, its internal processes such as geological activity or even biological evolution could be affected. For instance, a planet experiencing slower time might undergo geological changes at a much slower rate compared to a planet in a less intense gravitational field. This raises fascinating questions about the potential for life in such extreme environments. Could life adapt to a world where time itself is distorted? While this remains speculative, it's a thought-provoking idea that highlights the unique challenges and opportunities presented by Tredecuple systems. The study of time dilation in these systems also has broader implications for our understanding of the universe. By observing how time behaves in such extreme environments, scientists can test and refine the predictions of general relativity. Tredecuple systems, with their complex gravitational interactions, offer a natural testing ground for theories about the nature of space-time. They allow us to explore how gravity shapes not just the motion of stars and planets, but the very fabric of time itself. As we continue to unravel the mysteries of Tredecuple star systems, the phenomenon of time dilation serves as a powerful reminder of how strange and wondrous the universe can be. It challenges our perceptions of time and space, pushing the boundaries of what we thought was possible. And as we delve deeper into these cosmic enigmas, we may uncover even more extraordinary insights that reshape our understanding of reality. Next, we'll explore how Tredecuple systems compare to star clusters and what sets them apart in the grand tapestry of the cosmos. Now, let's turn our attention to a fascinating comparison that helps us better understand the unique nature of Tredecuple star systems. While they might seem similar at first glance, Tredecuple systems and star clusters are fundamentally different in their structure, behavior, and formation. Understanding these differences not only highlights the complexity of Tredecuple systems, but also sheds light on the diverse ways stars can come together in the cosmos. Star clusters are vast collections of stars, often numbering in the hundreds or even thousands, bound together by gravity. They come in two main types: open clusters and globular clusters. Open clusters are relatively young, loosely bound groups of stars that formed from the same molecular cloud. They are often found in the spiral arms of galaxies, including our own Milky Way. Globular clusters, on the other hand, are much older and denser, containing hundreds of thousands of stars packed into a spherical shape. These clusters orbit the centers of galaxies and are thought to be some of the oldest structures in the universe. Tredecuple star systems, in contrast, are much smaller and more tightly knit. As the name suggests, they consist of 13 stars gravitationally bound to one another. Unlike star clusters, which can span dozens or even hundreds of light years, tredecuple systems are compact, with stars orbiting each other in intricate patterns. This close proximity leads to intense gravitational interactions, making tredecuple systems far more dynamic and chaotic than star clusters. While star clusters are relatively stable over long periods, tredecuple systems are prone to dramatic changes, such as star ejections or collisions, due to the complex interplay of gravitational forces. Another key difference lies in their formation. Star clusters typically form from the collapse of a single massive molecular cloud, giving birth to hundreds or thousands of stars simultaneously. Tredecuple systems, however, likely form through a different process. One theory suggests that they originate from smaller groups of stars that gradually capture additional stars through gravitational interactions. This process results in a tightly bound system with a unique hierarchy of orbits, unlike the more uniform distribution of stars in a cluster. The dynamics of these systems also set them apart. In star clusters, stars move in relatively stable orbits around the cluster's center of mass, with occasional close encounters but few dramatic events. In tredecuple systems, the gravitational interactions are far more intense and frequent, leading to phenomena like unstable orbits, star cannibalism, and even the ejection of stars from the system. These interactions make tredecuple systems a hotbed of cosmic activity, offering scientists a unique opportunity to study the effects of extreme gravitational forces. Finally, the role of these systems in the broader universe differs significantly. Star clusters are often considered the building blocks of galaxies, playing a crucial role in star formation and galactic evolution. Tredecuple systems, while less common, provide valuable insights into the behavior of multiple star systems and the limits of gravitational interactions. They serve as natural laboratories for testing theories about star formation, orbital mechanics, and even the potential for life in complex stellar environments. By comparing tredecuple systems to star clusters, we gain a deeper appreciation for the incredible diversity of stellar arrangements in the universe. Each type of system offers its own set of mysteries and opportunities for discovery, reminding us that the cosmos is far more varied and intricate than we often imagine. Next, we'll delve into the discovery of ancient tredecuple systems and what they reveal about the early universe. Now, let's journey back in time to uncover one of the most intriguing discoveries about tredecuple star systems, their ancient origins. The existence of ancient tredecuple systems offers us a rare glimpse into the early universe, shedding light on how stars and stellar systems formed billions of years ago. These systems are like cosmic time capsules, preserving clues about the conditions and processes that shaped the universe in its infancy. One of the most remarkable ancient tredecuple systems discovered so far lies in a distant corner of the cosmos, dating back to when the universe was just a fraction of its current age. This system, observed through advanced telescopes and spectroscopic analysis, contains stars that are among the oldest ever detected. Their chemical composition reveals a lack of heavy elements, which tells us they formed before the universe had been enriched by the explosions of earlier generations of stars. This makes them invaluable for understanding the primordial era of star formation. The discovery of these ancient systems challenges some of our previous assumptions about how multiple star systems form and evolve. For instance, scientists once believed that complex systems like tredecupples required a universe rich in heavy elements to stabilize their orbits. However, the existence of ancient tredecupples suggests that even in the early universe, where such elements were scarce, the gravitational dance of stars could still create intricate and stable systems. This finding reshapes our understanding of the conditions necessary for the formation of multiple star systems. Another fascinating aspect of ancient tredecupples is their role in the cosmic timeline. These systems provide evidence that the universe was capable of forming complex structures much earlier than previously thought. By studying their orbits and interactions, scientists can piece together how gravitational forces operated in the early universe, offering insights into the fundamental laws of physics that govern the cosmos at that time. This information helps us refine our models of cosmic evolution and better understand the processes that led to the formation of galaxies and larger structures. Moreover, ancient tredecupples serve as natural laboratories for testing theories about star formation and stellar dynamics. Their longevity and stability, despite the chaotic environment of the early universe, suggest that these systems have unique properties that allowed them to survive for billions of years. By analyzing their behavior, researchers can explore how stars interact over vast timescales and how these interactions influence the evolution of stellar systems. The discovery of ancient tredecupples also raises intriguing questions about the early universe's capacity for complexity. If such intricate systems could form and endure in a time when the universe was far less structured than it is today, what other surprises might be waiting to be uncovered? These systems remind us that the cosmos is full of mysteries, and each discovery brings us closer to understanding the grand tapestry of the universe. As we continue to explore the depths of space, ancient tredecupples stand as a testament to the enduring nature of stellar systems and the incredible resilience of the universe itself. Next, we'll delve into the fascinating cycle of star death and rebirth within tredecuple systems, uncovering how these cosmic giants evolve over time. Now, shifting our gaze to the life cycles of stars within tredecuple systems, we uncover a mesmerizing process of death and rebirth that shapes the very fabric of these cosmic giants. In tredecuple systems, the death of a star is not an end but a dramatic transformation, setting the stage for new stellar life and continuing the cycle of cosmic evolution. When a star in a tredecuple system exhausts its nuclear fuel, it undergoes a spectacular death, often in the form of a supernova or a planetary nebula. These explosive events scatter the star's material across the system, enriching the surrounding space with heavy elements like carbon, oxygen, and iron. This stellar debris becomes the building blocks for new stars and planets, creating a cosmic recycling process that fuels the system's ongoing evolution. In some cases, the death of a star in a tredecuple system can trigger the birth of new stars. The shock waves from a supernova can compress nearby gas clouds, causing them to collapse under gravity and ignite into new stellar bodies. This process, known as triggered star formation, is particularly fascinating in tredecuple systems, where the gravitational interactions between multiple stars can amplify these effects. The result is a dynamic environment where the death of one star can lead to the birth of several others, creating a continuous cycle of stellar renewal. But the story doesn't end there. In tredecuple systems, the remnants of dead stars often play a crucial role in shaping the system's future. Neutron stars or black holes, formed from the cores of massive stars, can exert powerful gravitational influences on their surroundings. These remnants can pull in nearby material, creating accretion disks that emit intense radiation and sometimes even give rise to new stars or planets. In this way, the death of a star can set the stage for the emergence of entirely new cosmic structures. The cycle of star death and rebirth in tredecuple systems also highlights the interconnectedness of stellar evolution. The material ejected by dying stars not only forms new stars but also contributes to the formation of planets, asteroids, and other celestial bodies. This process creates a rich tapestry of cosmic diversity, where each generation of stars leaves its mark on the system's history. Over billions of years, this cycle of death and rebirth shapes the system's structure, influencing the orbits and interactions of its stars. What makes Tredecuple systems particularly unique is the sheer scale and complexity of these processes. With 13 stars interacting gravitationally, the death of one star can have far-reaching consequences for the entire system. For example, the explosion of a massive star can destabilize the orbits of nearby stars, leading to chaotic interactions or even the ejection of stars from the system. At the same time, the birth of new stars can introduce fresh dynamics, altering the system's gravitational balance and creating new opportunities for cosmic evolution. This cycle of star death and rebirth is not just a scientific curiosity, it's a fundamental aspect of how the universe evolves. By studying these processes in Tredecuple systems, scientists gain valuable insights into the life cycles of stars, the formation of planetary systems, and the forces that drive cosmic change. These systems serve as natural laboratories, offering a glimpse into the intricate dance of creation and destruction that shapes the cosmos. As we marvel at the resilience and adaptability of Tredecuple systems, we're reminded of the universe's capacity for renewal. Even in the face of stellar death, new life emerges, carrying forward the legacy of the stars that came before. Next, we'll explore the powerful magnetic fields generated by these systems and how they influence the behavior of stars and planets within them. Now, let's turn our attention to the invisible yet powerful forces that shape Tredecuple star systems, magnetic fields. In these systems, the presence of 13 stars means magnetic fields are not only stronger but also far more complex than those found in simpler star systems. Each star generates its own magnetic field, and when these fields interact, they create a web of magnetic forces that can influence everything from stellar behavior to the formation of planets. The magnetic fields in Tredecuple systems are shaped by the unique dynamics of multiple stars orbiting one another. As stars move through their intricate dance, their magnetic fields twist, stretch, and sometimes even collide. These interactions can produce spectacular phenomena, such as massive magnetic loops that stretch between stars or intense magnetic storms that ripple across the system. These storms can release bursts of energy, heating up nearby gas and dust and triggering new waves of star formation. One of the most fascinating aspects of these magnetic fields is their ability to channel and accelerate charged particles. In Tredecuple systems, the combined magnetic forces of multiple stars can act like cosmic particle accelerators, propelling particles to incredibly high speeds. These high-energy particles can then interact with the surrounding environment, creating glowing auroras around stars or even influencing the orbits of nearby planets. In some cases, these particles can escape the system entirely, contributing to the cosmic rays that permeate the universe. The magnetic fields in Tredecuple systems also play a crucial role in regulating stellar activity. For example, they can influence the rotation rates of stars, slowing them down or speeding them up depending on the strength and orientation of the magnetic forces. This, in turn, affects the stars' lifespans and the types of phenomena they produce, such as flares or sunspots. In systems with neutron stars or black holes, the magnetic fields can become even more extreme, generating powerful jets of particles that shoot out into space at nearly the speed of light. But the influence of magnetic fields doesn't stop at the stars themselves. They also shape the environment around them, affecting the formation and evolution of planets. In Tredecuple systems, the complex interplay of magnetic fields can create regions of intense radiation or turbulence, making it difficult for planets to form or survive. At the same time, these fields can also protect planets from harmful cosmic radiation, shielding them and potentially creating conditions suitable for life. Understanding the magnetic fields in Tredecuple systems is no easy task. Scientists rely on advanced simulations and observations to map these invisible forces and predict their effects. By studying these systems, researchers gain insights into how magnetic fields shape the universe, from the smallest particles to the largest structures. These findings not only deepen our understanding of Tredecuple systems, but also shed light on the fundamental processes that govern all star systems. As we explore the magnetic mysteries of Tredecuple systems, we're reminded of the unseen forces that drive the cosmos. These magnetic fields, though invisible, are a testament to the intricate and interconnected nature of the universe. Next, we'll delve into the high levels of cosmic radiation found in these systems and the challenges they pose for both stars and planets. Now, shifting our gaze to another intriguing aspect of Tredecuple star systems, let's explore the intense cosmic radiation that permeates these complex stellar environments. With 13 stars packed into a relatively small space, the levels of radiation in these systems are unlike anything found in simpler star systems. This radiation, a mix of high-energy particles and electromagnetic waves, is generated by the constant activity of the stars, from their nuclear fusion processes to their magnetic interactions. The sheer number of stars in a Tredecuple system means that radiation levels are amplified. Each star emits its own stream of particles and energy, and when combined, these emissions create a dense, chaotic radiation field. This radiation isn't just a byproduct of stellar activity. It plays a significant role in shaping the system's environment. For instance, the intense radiation can heat up surrounding gas and dust, influencing the formation of new stars or even preventing planets from forming in certain regions. One of the most striking effects of this radiation is its impact on the stability of the system. High-energy particles can collide with atoms in the surrounding space, creating secondary particles and further increasing the radiation levels. This creates a feedback loop where the radiation itself generates even more radiation. In some cases, this can lead to the creation of radiation belts, similar to Earth's Van Allen belts, but on a much larger and more intense scale. These belts can trap particles, creating zones of extreme radiation that pose significant hazards to any objects or potential life forms within the system. The hazards of cosmic radiation in Tredecuple systems are not to be underestimated. For planets or other celestial bodies, prolonged exposure to such high levels of radiation can strip away atmospheres, erode surfaces, and even disrupt the chemical processes necessary for life. Even for the stars themselves, the radiation can influence their evolution, altering their magnetic fields or triggering unusual stellar phenomena like flares or coronal mass ejections. Interestingly, the radiation in these systems also has a role in shaping the broader cosmic environment. Particles accelerated by the intense magnetic fields of Tredecuple systems can escape into interstellar space, contributing to the background radiation that permeates the galaxy. This means that the influence of these systems extends far beyond their immediate boundaries, affecting the larger universe in ways we are only beginning to understand. Scientists studying Tredecuple systems face significant challenges when it comes to measuring and analyzing this radiation. The complexity of the interactions between multiple stars and their radiation fields requires advanced simulations and observational techniques. By piecing together data from telescopes and space probes, researchers are slowly unraveling the mysteries of how cosmic radiation shapes these systems and what it means for the broader cosmos. As we continue to uncover the secrets of Tredecuple star systems, the role of cosmic radiation stands out as a key factor in their dynamics. From shaping stellar evolution to influencing the potential for life, this invisible force is a reminder of the powerful and often unseen processes that govern the universe. Next, we'll dive into the phenomenon of star cannibalism, where one star consumes another, and how this dramatic event plays out in the crowded environments of Tredecuple systems. Now, let's turn our attention to one of the most dramatic and fascinating phenomena in the cosmos, star cannibalism. In the crowded and chaotic environments of Tredecuple star systems, where 13 stars orbit in close proximity, the gravitational interactions can sometimes lead to one star consuming another. This process, known as star cannibalism, is a violent and awe-inspiring event that reshapes the system in profound ways. Star cannibalism occurs when a larger, more massive star gravitationally pulls material from a smaller companion star. Over time, the larger star strips away the outer layers of its neighbor, absorbing its gas and energy. This process can happen in several ways. In some cases, the stars are so close that their outer atmospheres touch, allowing the larger star to siphon material directly. In other cases, the gravitational pull of the larger star distorts the shape of the smaller one, stretching it into a teardrop-like form until material begins to flow between them. In Tredecuple systems, the likelihood of star cannibalism increases due to the sheer number of stars and their complex gravitational interactions. With so many stars in close quarters, the chances of two stars coming into close contact are much higher than in simpler systems. When this happens, the stronger star often dominates, leading to the gradual consumption of its companion. This process can take millions of years, but the effects are dramatic, altering the masses, compositions, and even the fates of the stars involved. One of the most striking outcomes of star cannibalism is the creation of exotic stellar remnants. For example, if a white dwarf star consumes material from a companion, it can trigger a runaway nuclear reaction, leading to a spectacular supernova explosion. Alternatively, if a neutron star is the cannibal, it can grow so massive that it collapses into a black hole. These events not only change the stars themselves, but also send ripples through the entire system, influencing the orbits and behaviors of the other stars. The prevalence of star cannibalism in Tredecuple systems also has implications for the system's overall evolution. As stars consume their neighbors, they grow more massive and luminous, altering the balance of gravitational forces within the system. This can lead to further instability, potentially triggering more cannibalistic events or even causing stars to be ejected from the system entirely. Over time, these processes can transform a Tredecuple system into something entirely different, with fewer stars and a new dynamic equilibrium. Scientists study star cannibalism by observing the telltale signs of these events, such as irregular brightness changes, unusual stellar compositions, or the presence of accretion, disk rings of material swirling around a star as it consumes its companion. These observations provide valuable insights into the life cycles of stars and the complex interactions that shape multi-star systems. As we continue to explore the mysteries of Tredecuple star systems, star cannibalism stands out as a powerful reminder of the dynamic and often violent nature of the cosmos. It's a process that not only reshapes individual stars but also influences the fate of entire systems, offering a glimpse into the intricate dance of gravity, energy, and matter that defines our universe. Next, we'll delve into the possibility of alien life in these extreme environments and the challenges it would face. Now, let's shift our gaze to one of the most intriguing questions in astronomy. Could alien life exist in the chaotic and extreme environments of Tredecuple star systems? While the idea of life thriving in such a complex and dynamic setting might seem far-fetched, the universe has a way of surprising us. Tredecuple systems, with their 13 stars and intricate gravitational dances, present both unique opportunities and formidable challenges for the emergence and survival of life. One of the biggest hurdles for life in these systems is the extreme variability of conditions. With so many stars in close proximity, planets orbiting within a Tredecuple system would experience wildly fluctuating temperatures and radiation levels. Imagine a world where the sun rises and sets multiple times a day, each star casting its own light and heat. The constant shifts in energy could make it difficult for stable ecosystems to develop, as life would need to adapt to an environment that changes dramatically over short periods. Another challenge is the intense gravitational forces at play. The gravitational tug-of-war between 13 stars could destabilize planetary orbits, making it hard for a planet to maintain a stable climate over long periods. A planet might be pulled into a highly elliptical orbit, swinging close to one star and then far away, leading to extreme temperature swings. Alternatively, it could be ejected from the system entirely, becoming a rogue planet drifting through the cold void of space. For life to exist, it would need to endure these chaotic conditions or find a way to thrive in the brief moments of stability. Despite these challenges, there are scenarios where life might still find a way. Some planets in Tredecuple systems could orbit a single star at a safe distance, shielded from the worst of the gravitational chaos. These stars might act as anchors, providing a relatively stable environment for life to develop. Additionally, the presence of multiple stars could create unique niches for life. For example, a planet orbiting one star might receive occasional bursts of energy from nearby stars, potentially driving the evolution of life forms that can harness these energy spikes. The diversity of stars in Tredecuple systems also opens up intriguing possibilities. With stars of different sizes, temperatures, and ages, there could be a wide range of habitable zones, regions where conditions are just right for liquid water to exist. Life might emerge on a planet orbiting a cooler, dimmer star, while another planet circling a hotter, brighter star could develop entirely different forms of life. The sheer variety of environments within a single system could lead to a rich tapestry of life, each adapted to its own unique conditions. However, the presence of life in these systems would likely be very different from what we know on Earth. Organisms might evolve to withstand extreme radiation, rapid temperature changes, or even periods of complete darkness. They could develop unique survival strategies, such as hibernating during harsh conditions or thriving in environments where energy is sporadic. The possibility of life in Tredecuple systems challenges our understanding of what life can endure and where it might exist. Scientists are particularly interested in the potential for life on moons orbiting gas giants within these systems. A moon with a thick atmosphere could shield life from the worst of the radiation and gravitational disturbances, while tidal forces from its host planet might provide enough heat to sustain liquid water. Such moons could serve as cosmic oases, offering a stable environment for life to flourish despite the chaos of the surrounding system. As we ponder the possibility of alien life in Tredecuple systems, it's clear that these environments push the boundaries of what we consider habitable. While the challenges are immense, the potential rewards are equally profound. Discovering life in such extreme conditions would not only expand our understanding of biology, but also redefine our place in the universe. Next, we'll explore how the detection of gravitational waves from Tredecuple systems is shedding new light on these cosmic mysteries. Now, let's dive into a discovery that has revolutionized our understanding of the cosmos: gravitational waves from Tredecuple star systems. These ripples in space-time, first predicted by Albert Einstein over a century ago, are not just a fascinating phenomenon, but also a powerful tool for studying the universe's most extreme environments. When it comes to Tredecuple systems, gravitational waves offer a unique window into the chaotic and dynamic interactions between their 13 stars. The detection of gravitational waves from these systems is no small feat. The complex gravitational interactions between so many stars create a symphony of ripples that travel across the universe. These waves are generated by massive events such as the collision or merger of stars, or even the rapid spinning of neutron stars within the system. Each event sends out a unique signature, allowing scientists to piece together the story of what's happening in these distant and crowded star systems. One of the most significant aspects of detecting gravitational waves from Tredecuple systems is the insight they provide into the behavior of gravity itself. In such a densely packed environment, the gravitational forces are incredibly intense and constantly shifting. By studying the waves produced, researchers can test and refine our understanding of how gravity operates under extreme conditions. This not only confirms Einstein's theory of general relativity, but also helps us explore potential deviations that could hint at new physics. Another exciting implication is the ability to map the structure of Tredecuple systems in unprecedented detail. Gravitational waves carry information about the masses, distances, and movements of the objects that produce them. For Tredecuple systems, this means we can uncover the intricate dance of stars, revealing how they orbit each other, how close they come to colliding, and even how they influence the formation of planets or other celestial bodies within the system. It's like listening to a cosmic orchestra and decoding the music to understand the instruments and their movements. The detection of these waves also opens up new possibilities for observing phenomena that are otherwise invisible. For example, black holes within Tredecuple systems which emit no light can be detected through the gravitational waves they produce when interacting with other stars or merging with one another. This allows scientists to study these mysterious objects in a way that traditional telescopes cannot, shedding light on their role in shaping the dynamics of Tredecuple systems. Perhaps one of the most profound implications is the potential to uncover the origins of these systems. Gravitational waves can reveal clues about how Tredecuple systems form and evolve over time. Did they start as smaller star clusters that merged, or were they born from a single massive cloud of gas and dust that fragmented into 13 stars? By analyzing the waves, scientists can piece together the history of these systems, offering a glimpse into the processes that shape the universe on a grand scale. As we continue to detect and study gravitational waves from Tredecuple systems, we're not just observing the universe, we're listening to it. Each ripple tells a story, and together they paint a picture of a cosmos that is far more dynamic and interconnected than we ever imagined. Next, we'll explore the extreme temperature variations among stars in these systems and what they reveal about the nature of these cosmic giants. Now, let's turn our attention to a discovery that showcases the incredible diversity within Tredecuple star systems, the extreme temperature variations among their stars. Imagine a cosmic neighborhood where some stars burn with the heat of a raging inferno, while others glow faintly like embers in the night. This stark contrast in temperatures is not just a fascinating spectacle, but also a key to understanding the complex dynamics of these systems. In Tredecuple systems, the range of temperatures among stars can be staggering. Some stars, like hypergiants, can reach surface temperatures of tens of thousands of degrees Celsius, radiating intense heat and light. On the other end of the spectrum, smaller stars, such as red dwarfs, may have surface temperatures as low as a few thousand degrees, appearing cooler and dimmer. This wide variation is a direct result of the different masses, ages, and evolutionary stages of the stars within the system. One of the primary factors driving these temperature extremes is the mass of the stars. More massive stars burn their nuclear fuel at a much faster rate, generating immense heat and pressure in their cores. This rapid consumption of fuel leads to higher surface temperatures and shorter lifespans. In contrast, smaller stars burn their fuel more slowly, resulting in cooler temperatures and longer lives. In a Tredecuple system where stars of vastly different masses coexist, this creates a dramatic range of temperatures. Another factor contributing to temperature variations is the age of the stars. Younger stars, still in the process of forming, can exhibit fluctuating temperatures as they settle into stable nuclear fusion. Older stars nearing the end of their life cycles may undergo dramatic changes in temperature as they expand into giants or collapse into dense remnants like neutron stars. In a Tredecuple system where stars of different ages are packed closely together, these temperature shifts can create a dynamic and ever-changing environment. The interactions between stars in these systems also play a role in shaping their temperatures. Gravitational forces can cause stars to draw material from one another, altering their mass and consequently their temperature. For example, a star that gains mass from a companion may heat up and become more luminous, while the donor star may cool as it loses material. These exchanges can lead to sudden and extreme temperature changes, adding another layer of complexity to the system. Interestingly, the extreme temperature variations in Tredecuple systems can also influence the surrounding space. Hotter stars emit powerful stellar winds and radiation, which can heat up nearby gas and dust, while cooler stars may allow these materials to condense and form new stars or planets. This interplay between temperature extremes and the surrounding environment makes Tredecuple systems a fascinating laboratory for studying star formation and evolution. As we continue to explore these systems, the study of temperature variations offers valuable insights into the life cycles of stars and the forces that shape their environments. From the blazing heat of hypergiants to the cool glow of red dwarfs, each star tells a story of cosmic evolution. Next, we'll delve into the role of cosmic dust clouds in Tredecuple systems and how they obscure our observations of these stellar wonders. Now, shifting our gaze to the cosmic dust clouds that envelop Tredecuple star systems, we uncover another layer of mystery and complexity. These vast clouds of gas and dust, often spanning light years, play a crucial role in shaping the environment of these systems while simultaneously hiding their secrets from our telescopes. Cosmic dust clouds are not just passive observers in the drama of Tredecuple systems, they are active participants. These clouds are composed of tiny particles, including silicates, carbon compounds, and ice, which scatter and absorb light from the stars within the system. This scattering effect can make it incredibly challenging for astronomers to observe the stars directly, as the dust dims their light and distorts their appearance. In some cases, the dust is so thick that entire stars are completely obscured, leaving only faint hints of their presence. But these clouds are more than just cosmic curtains. They are also the birthplaces of new stars and planets. Within the dense regions of these clouds, gravity pulls material together, forming clumps that eventually collapse under their own weight. As these clumps grow denser and hotter, they ignite nuclear fusion, giving birth to new stars. In Tredecuple systems, where multiple stars are already present, this process can lead to the formation of even more stars, adding to the system's complexity. The interaction between the stars and the dust clouds is a dynamic and ongoing process. The intense radiation and stellar winds from the hotter stars can heat the surrounding dust, causing it to glow in infrared light. This infrared glow is often the only way astronomers can detect the presence of stars hidden behind the dust. At the same time, the cooler stars in the system may allow the dust to condense and form new structures, such as protoplanetary disks or even planets. One of the most fascinating aspects of these dust clouds is their ability to act as cosmic time capsules. The particles within the clouds can trap elements and compounds that were present during the formation of the system, preserving a record of its history. By studying the composition of these dust clouds, scientists can gain insights into the conditions that existed when the system first formed, as well as the processes that have shaped it over billions of years. Despite their challenges, cosmic dust clouds also offer unique opportunities for discovery. For example, the way light interacts with the dust can reveal information about the size, shape, and composition of the particles. This, in turn, can help astronomers understand the physical conditions within the system and how they influence star formation and evolution. As we peer through these cosmic veils, we are reminded of the intricate balance between visibility and obscurity in the universe. The dust clouds that hide the stars also hold the keys to unlocking their secrets, offering a tantalizing glimpse into the hidden workings of Tredecuple star systems. Next, we'll explore the wide range of star ages within these systems and what they reveal about their formation and evolution. Now, let's turn our attention to the fascinating disparities in star ages found within Tredecuple systems. Unlike simpler star systems where stars often form around the same time, Tredecuple systems can host stars of vastly different ages, ranging from newborn stars still shrouded in their birth clouds to ancient stars nearing the end of their lifespans. This wide range of ages offers a unique window into the formation and evolution of these complex systems. The presence of stars with such varied ages suggests that Tredecuple systems are not formed in a single, brief event. Instead, they likely undergo multiple episodes of star formation over billions of years. In some cases, older stars may have formed first, with younger stars emerging later from the remnants of earlier star-forming activity. This staggered formation process could be driven by the gravitational interactions between the stars themselves, which can compress nearby gas and dust, triggering new rounds of star birth. One of the most intriguing aspects of these age disparities is what they reveal about the system's history. For example, the presence of very old stars indicates that the system has existed for a long time, possibly since the early days of the universe. These ancient stars can serve as cosmic fossils, preserving information about the conditions that existed when the system first formed. On the other hand, younger stars provide clues about more recent events, such as collisions or close encounters that may have reignited star formation. The coexistence of stars with such different ages also has profound implications for the system's dynamics. Older stars, which have had more time to evolve, may have already gone through phases like supernova explosions or the formation of black holes, altering the gravitational landscape of the system. Meanwhile, younger stars are still in the process of settling into stable orbits, adding to the system's overall complexity and unpredictability. This mix of ages also raises questions about the potential for planets within Tredecuple systems. Planets orbiting older stars may have had more time to develop complex environments, while those around younger stars might still be in the early stages of formation. The interplay between stars of different ages could create a dynamic and ever-changing environment where planets face unique challenges and opportunities for survival. By studying these age disparities, astronomers can piece together the life story of Tredecuple systems, from their chaotic beginnings to their ongoing evolution. Each star, regardless of its age, contributes to the system's intricate tapestry, offering clues about the forces that have shaped it over time. As we continue to explore these systems, we gain a deeper understanding of how such complex structures arise and evolve in the cosmos. Next, we'll delve into the presence of binary star pairs within Tredecuple systems and how their interactions add another layer of complexity to these cosmic wonders. Now, let's shift our focus to the intriguing presence of binary star pairs within Tredecuple systems. These pairs, consisting of two stars orbiting a common center of mass, add yet another layer of complexity to these already intricate systems. While Tredecuple systems are defined by their 13 stars, it's not uncommon to find smaller groupings like binary pairs nestled within the larger structure. These pairs can form tight, stable orbits, creating mini-systems within the chaos of the Tredecuple arrangement. The interactions between binary pairs and the other stars in the system are nothing short of fascinating. Gravitational forces from the surrounding stars can influence the orbits of these pairs, sometimes pulling them closer together or pushing them farther apart. In some cases, the gravitational tug-of-war can even destabilize the binary pair, leading to dramatic events like one star being ejected from the system or, in rare instances, a collision between the two stars. These interactions highlight the delicate balance that exists within Tredecuple systems, where even small changes can have significant consequences. One of the most remarkable aspects of binary pairs in Tredecuple systems is their ability to act as gravitational anchors. Their strong mutual attraction can help stabilize the orbits of nearby stars, preventing the system from descending into complete chaos. At the same time, their presence can also introduce new sources of instability, as their gravitational influence can disrupt the paths of other stars. This duality makes binary pairs both a stabilizing and destabilizing force within these systems, adding to their dynamic nature. The study of binary pairs within Tredecuple systems also provides valuable insights into the formation and evolution of these cosmic structures. In some cases, binary pairs may have formed independently before being captured by the larger system, while in others, they could have emerged from the same cloud of gas and dust that gave birth to the Tredecuple system. By analyzing the orbits and compositions of these pairs, astronomers can piece together the history of the system and better understand the processes that shaped it. Interestingly, binary pairs can also influence the potential for planets within Tredecuple systems. Planets orbiting one of the stars in a binary pair face unique challenges such as extreme temperature variations and complex gravitational forces. However, they also offer unique opportunities, as the gravitational interplay between the two stars could create stable regions where planets might thrive. The presence of binary pairs adds another dimension to the already complex question of habitability in these systems. As we continue to explore Tredecuple systems, the role of binary pairs remains a key area of interest. Their interactions not only shape the dynamics of the system, but also provide a window into the processes that govern the formation and evolution of these cosmic wonders. Next, we'll explore how stars can be ejected from Tredecuple systems due to gravitational interactions, shedding light on the forces that drive these dramatic events. Now, let's turn our attention to one of the most dramatic phenomena in Tredecuple star systems: star ejections. Imagine a cosmic game of tug-of-war, where the gravitational pull of multiple stars competes for dominance. In these densely packed systems, stars are constantly influenced by the gravitational forces of their neighbors, and sometimes this interplay can become so intense that a star is flung out of the system entirely. This process, known as stellar ejection, is a testament to the chaotic and dynamic nature of Tredecuple systems. The ejection of a star typically occurs when gravitational interactions between stars become unbalanced. For instance, if a star passes too close to a binary pair or a group of tightly bound stars, the combined gravitational forces can accelerate it to incredible speeds. In some cases, this acceleration is so extreme that the star breaks free from the system's gravitational grip, hurtling into the void of interstellar space. These ejected stars, often referred to as runaway stars, can travel at velocities of hundreds of kilometers per second, leaving their former companions behind. What makes star ejections particularly fascinating is their impact on the remaining system. When a star is ejected, it carries away a portion of the system's energy and momentum. This loss can alter the orbits of the remaining stars, sometimes leading to further instability. In some cases, the ejection of one star can trigger a chain reaction, causing additional stars to be flung out of the system. This domino effect highlights the delicate balance within Tredecuple systems, where even a single event can have far-reaching consequences. Interestingly, ejected stars aren't just a byproduct of chaos, they also serve as cosmic messengers. By studying the trajectories and velocities of these runaway stars, astronomers can trace their origins back to the Tredecuple systems they once belonged to. This information provides valuable clues about the gravitational interactions that led to their ejection, offering insights into the internal dynamics of these complex systems. Additionally, ejected stars can carry with them remnants of the system's history, such as chemical signatures or traces of planetary material, further enriching our understanding of their origins. The phenomenon of star ejections also raises intriguing questions about the long-term evolution of Tredecuple systems. Over time, repeated ejections could lead to the gradual disintegration of the system as stars are lost one by one. Alternatively, the loss of stars might stabilize the remaining system, reducing the likelihood of further ejections. Understanding these processes is crucial for unraveling the life cycle of Tredecuple systems and their ultimate fate. As we delve deeper into the mysteries of Tredecuple systems, the ejection of stars stands out as a vivid reminder of the immense forces at play in the cosmos. These events not only shape the systems themselves but also contribute to the broader tapestry of the universe, scattering stars across the galaxy and influencing the evolution of interstellar space. Next, we'll explore the stunning visual phenomena that occur in these systems, from flares to explosions, as we uncover the cosmic fireworks that light up Tredecuple star systems. Now, let's shift our gaze to the dazzling spectacle of cosmic fireworks within Tredecuple star systems. These systems are not just chaotic, they are also home to some of the most breathtaking visual phenomena in the universe. Imagine a celestial stage where stars unleash bursts of energy, creating flares and explosions that light up the darkness of space. These events are not only visually stunning but also scientifically significant, offering a window into the extreme conditions that define Tredecuple systems. One of the most dramatic displays in these systems is the occurrence of stellar flares. These are sudden, intense bursts of radiation that erupt from the surfaces of stars, often triggered by the complex interplay of magnetic fields. In Tredecuple systems, where multiple stars are in close proximity, the magnetic interactions can become incredibly intense. When the magnetic fields of two or more stars interact, they can twist and snap, releasing enormous amounts of energy in the form of flares. These flares can outshine the stars themselves for brief moments, creating a brilliant flash that can be observed across vast distances. But flares are just the beginning. Tredecuple systems are also prone to massive stellar explosions, such as supernovae. When a star in one of these systems reaches the end of its life, it can explode in a cataclysmic event that sends shockwaves through the surrounding space. The sheer number of stars in a Tredecuple system increases the likelihood of such explosions, making these systems a hotbed for cosmic fireworks. The aftermath of a supernova can leave behind a neutron star or even a black hole, adding another layer of complexity to the system. Another fascinating phenomenon is the collision of stars. In the crowded environment of a Tredecuple system, stars can sometimes come too close to one another, leading to direct collisions. When this happens, the result is a spectacular explosion that can outshine entire galaxies for a brief period. These collisions release vast amounts of energy and can trigger the formation of new stars or even planetary systems, further enriching the cosmic landscape. The visual impact of these events is not just limited to the immediate vicinity of the Tredecuple system. The light and radiation from flares, supernovae, and collisions can travel across the galaxy, illuminating distant regions of space. For astronomers, these events serve as natural laboratories, providing insights into the processes that govern the life and death of stars. By studying the light and radiation emitted during these cosmic fireworks, scientists can learn more about the composition, temperature, and dynamics of the stars involved. What makes these phenomena even more intriguing is their unpredictability. In Tredecuple systems, the gravitational interactions between stars are so complex that predicting when and where a flare or explosion will occur is nearly impossible. This unpredictability adds an element of excitement to the study of these systems, as astronomers never know when the next cosmic firework will light up the sky. As we marvel at the beauty of these cosmic fireworks, it's important to remember that they are more than just visual spectacles. They are a testament to the dynamic and ever-changing nature of Tredecuple star systems. Each flare, explosion, and collision tells a story of the forces that shape the universe, offering us a glimpse into the incredible power and complexity of the cosmos. Next, we'll explore the varying spin rates of stars in these systems and how they influence the overall dynamics of Tredecuple systems. Now, let's turn our attention to the fascinating world of star spin rates within Tredecuple systems. Just like dancers in a cosmic ballet, stars in these systems spin at wildly different speeds, creating a dynamic and ever-changing environment. The spin rate of a star, or how fast it rotates on its axis, plays a crucial role in shaping its behavior and the overall dynamics of the system. In Tredecuple systems, where multiple stars interact closely, these spin rates can vary dramatically, leading to some truly extraordinary effects. One of the most striking aspects of star spin rates in Tredecuple systems is their sheer diversity. Some stars spin slowly, taking weeks or even months to complete a single rotation, while others whirl around at breakneck speeds, completing a full spin in just a matter of hours. This variation is often influenced by the star's age, mass, and its interactions with neighboring stars. Younger stars, for example, tend to spin faster due to the conservation of angular momentum from their formation, while older stars may slow down over time as they lose energy. The spin rate of a star also has a direct impact on its magnetic field. Faster spinning stars generate stronger magnetic fields, which can lead to intense stellar activity such as flares and sunspots. In Tredecuple systems, where stars are in close proximity, these magnetic fields can interact in complex ways, sometimes leading to spectacular displays of energy. For instance, when two stars with strong magnetic fields come close to each other, their fields can twist and reconnect, releasing bursts of energy that light up the surrounding space. But the effects of varying spin rates don't stop there. The spin of a star also influences its shape. Stars spinning at extremely high speeds can become oblate, meaning they bulge at the equator and flatten at the poles. This distortion can affect the star's gravitational pull, potentially altering the orbits of nearby stars or even planets within the system. In Tredecuple systems, where gravitational interactions are already complex, these shape changes add another layer of intricacy to the cosmic dance. Another intriguing consequence of differing spin rates is the potential for star collisions. In a Tredecuple system where stars are packed closely together, a fast-spinning star might lose stability over time, increasing the likelihood of a collision with a neighboring star. Such collisions can trigger massive explosions, reshaping the system and giving birth to new stars or even black holes. These events not only alter the physical structure of the system, but also release vast amounts of energy, influencing the surrounding space for light years. The study of star spin rates in Tredecuple systems also provides valuable insights into the life cycles of stars. By observing how spin rates change over time, astronomers can piece together the history of these systems, understanding how they formed and evolved. For example, a star that spins unusually fast might be the result of a past collision or merger, offering clues about the system's turbulent past. As we delve deeper into the mysteries of Tredecuple systems, the varying spin rates of stars remind us of the incredible diversity and complexity of the cosmos. Each star, with its unique rotation, contributes to the intricate web of interactions that define these systems. Next, we'll explore how sound waves travel through the plasma in these systems and what they reveal about the hidden dynamics of Tredecuple star systems. Now, let's shift our focus to a phenomenon that might sound almost otherworldly: cosmic sound waves. In the vast expanse of Tredecuple star systems, sound waves travel through the plasma that fills the space between stars, creating a symphony of vibrations that reveal hidden secrets about these complex systems. Unlike sound on Earth, which travels through air, cosmic sound waves move through the superheated, ionized gas known as plasma, which is abundant in these star-filled environments. The way sound waves behave in Tredecuple systems is truly fascinating. As stars interact with one another, their gravitational forces and magnetic fields create ripples in the surrounding plasma. These ripples or sound waves can travel vast distances, carrying information about the star's movements, temperatures, and even their internal structures. By studying these waves, astronomers can gain insights into the dynamics of the system that would otherwise remain invisible. One of the most intriguing aspects of cosmic sound waves is their ability to act as natural probes. As these waves travel through the plasma, they interact with the stars and other materials in their path, causing subtle changes in their frequency and amplitude. These changes can be detected by sensitive instruments, allowing scientists to map the density and temperature of the plasma, as well as the positions and movements of the stars themselves. It's like listening to an echo in a cavern, but on a cosmic scale. The study of these sound waves has also revealed the presence of phenomena such as plasma oscillations and shock waves. For example, when two stars in a Tredecuple system come close to each other, their gravitational pull can create shock waves that ripple through the plasma, producing bursts of energy detectable across vast distances. These shock waves can even trigger star formation in nearby regions, adding new members to the already crowded system. Another remarkable discovery is the role of sound waves in regulating the temperature of the plasma. In Tredecuple systems where stars are packed closely together, the plasma can become incredibly hot. Sound waves help distribute this heat more evenly, preventing extreme temperature variations that could destabilize the system. This balancing act is crucial for maintaining the delicate gravitational equilibrium that keeps the stars in their intricate orbits. Cosmic sound waves also provide clues about the age and evolution of Tredecuple systems. By analyzing the patterns and frequencies of these waves, astronomers can estimate how long the system has existed and how it has changed over time. For instance, older systems tend to have more complex wave patterns, reflecting the numerous interactions and collisions that have occurred over billions of years. As we explore the hidden world of cosmic sound waves, we gain a deeper appreciation for the complexity and beauty of Tredecuple star systems. These waves are not just vibrations in space. They are messengers carrying stories of stellar interactions, gravitational dances, and the ever-changing nature of the cosmos. Next, we'll delve into the wide range of star masses within these systems and how their gravitational effects shape the destiny of Tredecuple systems. Now, let's turn our attention to another fascinating aspect of Tredecuple star systems: the incredible diversity in star masses. In these complex systems, stars can vary dramatically in size and mass, from tiny red dwarfs to massive hypergiants. This wide range of masses creates a dynamic gravitational environment, where the pull of each star influences the others in ways that are both chaotic and mesmerizing. The gravitational effects of these mass disparities are profound. In a Tredecuple system, the most massive stars often dominate the gravitational landscape, pulling smaller stars into their orbits and shaping the overall structure of the system. However, the smaller stars aren't just passive participants. They also exert their own gravitational influence, creating a delicate balance of forces that keeps the system in motion. This interplay of gravitational pulls can lead to fascinating phenomena, such as stars being flung into highly elliptical orbits or even ejected from the system entirely. One of the most striking consequences of these mass disparities is the way they affect the stability of the system. While the gravitational pull of massive stars can help anchor the system, the presence of smaller, faster-moving stars can introduce instability. These smaller stars often move at higher velocities, and their interactions with larger stars can create ripples in the gravitational field, leading to unpredictable changes in the system's structure over time. It's a cosmic tug-of-war where the balance of power is constantly shifting. The range of star masses also plays a key role in the evolution of Tredecuple systems. Over time, the most massive stars burn through their fuel quickly, ending their lives in spectacular supernovae or collapsing into black holes. These dramatic events can send shockwaves through the system, altering the gravitational dynamics and triggering new rounds of star formation. Meanwhile, smaller stars can survive for billions of years, quietly orbiting their more massive counterparts and contributing to the system's long-term stability. Interestingly, the mass disparities in Tredecuple systems also provide astronomers with valuable clues about their formation. The presence of stars with such a wide range of masses suggests that these systems likely formed from massive clouds of gas and dust that fragmented unevenly, giving rise to stars of different sizes. By studying the distribution of star masses, scientists can piece together the history of these systems and better understand the processes that shape them. As we explore the gravitational effects of star mass disparities, we gain a deeper appreciation for the intricate balance that defines Tredecuple systems. These systems are not just random collections of stars, they are carefully choreographed cosmic dances, where the interplay of mass and gravity creates a dynamic and ever-changing spectacle. Next, we'll uncover how the alignment of stars in these systems can create unique shadow phenomena, adding yet another layer of mystery to these already fascinating structures. Now, let's step into the realm of cosmic shadows, where the alignment of stars in Tredecuple systems paints a breathtaking picture of light and darkness. Imagine a system where 13 stars orbit one another, their paths crossing and intertwining in a celestial ballet. When these stars align just right, they cast shadows across the void, creating phenomena that are as mysterious as they are beautiful. In Tredecuple systems, the sheer number of stars means that alignments are not only possible but frequent. When one star passes in front of another from our vantage point, it can block out its light, creating a temporary eclipse. But in a Tredecuple system, these eclipses are far more complex. Multiple stars can align in such a way that their shadows overlap, creating intricate patterns of light and dark that shift and change over time. These cosmic shadows can stretch across vast distances, sometimes even obscuring entire regions of the system. What makes these shadow phenomena truly unique is the way they interact with the surrounding space. The light from one star can be bent and distorted by the gravity of another, creating lensing effects that magnify or warp the shadows. This gravitational lensing can produce stunning visual effects such as rings of light or multiple images of the same star. These effects are not just beautiful to observe, they also provide valuable information about the masses and positions of the stars involved. The shadows in Tredecuple systems can also reveal hidden details about the structure of the system itself. By studying how light is blocked or bent, astronomers can map out the orbits of the stars and even detect the presence of planets or other objects that might otherwise go unnoticed. These shadows act like cosmic X-rays, allowing us to peer into the heart of the system and uncover its secrets. But the beauty of these shadow phenomena goes beyond their scientific value. They remind us of the delicate balance that exists in Tredecuple systems, where the interplay of light and gravity creates a constantly shifting tapestry of shadows and illumination. It's a reminder that even in the vastness of space, there is a kind of cosmic artistry at work, where the alignment of stars can create moments of breathtaking beauty. As we marvel at these cosmic shadows, we're reminded of the complexity and wonder of Tredecuple systems. These systems are not just collections of stars, they are living, breathing entities where the interplay of light and shadow tells a story of gravity, motion, and the passage of time. Next, we'll explore the unusual surface features of stars in these systems, where massive sunspots and flares reveal even more about the dynamic nature of these celestial giants. Now, shifting our gaze from the cosmic shadows, let's zoom in closer to the stars themselves, where the surfaces of these celestial giants reveal a world of chaos and wonder. In Tredecuple star systems, the surface features of stars are anything but ordinary. These stars, locked in a gravitational dance with their companions, often exhibit extreme and unusual characteristics that set them apart from stars in simpler systems. One of the most striking features is the presence of massive sunspots, dark, cooler regions on a star's surface caused by intense magnetic activity. In Tredecuple systems, these sunspots can be far larger and more frequent than those found on stars like our Sun. Imagine sunspots so vast they could swallow entire planets, stretching across the star's surface like cosmic scars. These sunspots are not just visually dramatic, they also play a crucial role in shaping the star's magnetic environment, influencing everything from solar winds to the star's overall stability. But sunspots are just the beginning. The stars in Tredecuple systems are also prone to frequent and powerful stellar flares. These flares are sudden bursts of energy that erupt from the star's surface, releasing immense amounts of radiation and charged particles into space. In a Tredecuple system, the gravitational interactions between stars can amplify this activity, leading to flares that are far more intense and frequent than those seen in single or binary star systems. These flares can light up the surrounding space, creating dazzling displays of energy that can be observed from great distances. What makes these flares particularly fascinating is their impact on the system as a whole. The radiation and particles released during a flare can interact with the magnetic fields of nearby stars, triggering a chain reaction of activity across the system. This interconnected web of magnetic interactions can lead to phenomena like coronal mass ejections, where massive amounts of plasma are hurled into space, or even the creation of shock waves that ripple through the system. The surface features of stars in Tredecuple systems also provide valuable clues about their internal dynamics. For example, the size and frequency of sunspots can reveal information about the star's rotation rate and magnetic field strength. Similarly, the intensity of flares can indicate the level of magnetic stress within the star, offering insights into its overall health and stability. By studying these features, astronomers can piece together a more complete picture of how stars in Tredecuple systems evolve and interact over time. As we explore these surface features, we're reminded of the dynamic and ever-changing nature of Tredecuple systems. Each star is a living, breathing entity, its surface a canvas of magnetic storms, fiery eruptions, and dark, brooding sunspots. These features not only add to the beauty of these systems, but also deepen our understanding of the complex forces at work within them. Next, we'll dive into the cosmic wind patterns generated by these stars, where the interplay of stellar winds creates a symphony of motion and energy that shapes the entire system. Now, let's turn our attention to the cosmic wind patterns that swirl through Tredecuple star systems, shaping the environment in ways that are both beautiful and chaotic. In these systems, the winds generated by multiple stars don't just blow in isolation, they collide, merge, and interact, creating a dynamic and ever-changing tapestry of motion and energy. These stellar winds, streams of charged particles ejected from the surfaces of stars, are far more intense than those found in simpler systems, and their interactions can have profound effects on the entire system. Each star in a Tredecuple system contributes its own unique wind, driven by factors like its size, temperature, and magnetic activity. For example, a massive hypergiant might produce a wind so powerful it can strip away the atmospheres of nearby stars, while a smaller, cooler star might generate a gentler breeze. When these winds meet, they create shock waves and turbulence, carving out vast regions of space filled with swirling plasma and magnetic fields. These interactions can even lead to the formation of intricate structures like bow shocks or wind bubbles, which can stretch for light years across the system. The impact of these cosmic wind patterns goes beyond just visual spectacle. They play a crucial role in shaping the environment of the system, influencing everything from the formation of new stars to the behavior of existing ones. For instance, the collision of stellar winds can compress gas and dust, triggering the birth of new stars or even entire star clusters. At the same time, the intense radiation and particles carried by these winds can erode the surfaces of planets or other stars, stripping away their atmospheres and altering their evolution. One of the most fascinating aspects of these wind patterns is their ability to act as cosmic messengers, carrying information about the stars that produce them. By studying the speed, density, and composition of these winds, astronomers can learn about the internal processes of the stars, such as their rotation rates, magnetic fields, and even their ages. This information provides valuable insights into how stars in Tredecuple systems evolve and interact over time, helping us piece together the complex puzzle of these cosmic giants. As we explore these wind patterns, we're reminded of the interconnected nature of Tredecuple systems. Each star's wind is a thread in a larger cosmic tapestry, woven together by gravity and magnetism to create a system that is both chaotic and harmonious. These winds not only shape the physical environment of the system, but also serve as a testament to the incredible forces at work within it. Next, we'll delve into the varying densities of stars in these systems, where the interplay of mass and gravity creates a delicate balance that defines the system's structure and evolution. Now, shifting our gaze to the stars themselves, let's explore the fascinating variations in density that define Tredecuple star systems. In these complex systems, stars aren't just scattered randomly, they exist in a delicate balance of mass and gravity, with densities that can vary dramatically from one star to the next. This diversity in density isn't just a curiosity. It plays a critical role in shaping the behavior and evolution of the entire system. Take, for instance, a massive hypergiant star. These colossal stars are incredibly dense at their cores, where nuclear fusion generates immense energy, but their outer layers can be surprisingly diffuse, stretching out into vast, tenuous atmospheres. On the other end of the spectrum, you might find a neutron star, a remnant of a supernova explosion, where matter is packed so tightly that a single teaspoon of its material would weigh billions of tons. Between these extremes, stars of all sizes and densities coexist, each contributing to the gravitational dance that defines a Tredecuple system. These density variations have profound implications for the system as a whole. For one, they influence how stars interact with each other. A denser star, like a neutron star, exerts a stronger gravitational pull, potentially disrupting the orbits of nearby stars or even pulling them into closer, more unstable paths. Meanwhile, less dense stars, like red giants, might be more easily influenced by the gravitational forces of their neighbors, leading to dramatic changes in their trajectories over time. The density of a star also affects its lifespan and ultimate fate. Denser stars, such as neutron stars or white dwarfs, are often the remnants of stellar explosions, marking the end of a star's life cycle. In contrast, less dense stars, like young protostars or aging red giants, are still in the process of evolving, their densities changing as they burn through their fuel and expand or contract. This interplay of density and evolution creates a dynamic environment where stars are constantly influencing each other, shaping the system's structure and future. But the implications don't stop there. The varying densities of stars in Tredecuple systems also affect the surrounding space. Denser stars, with their intense gravitational fields, can warp the fabric of space-time, creating gravitational lenses that bend light and distort our view of distant objects. Less dense stars, with their expansive atmospheres, can contribute to the formation of cosmic dust clouds or even trigger new star formation as their winds collide with surrounding gas and dust. As we consider these density variations, we're reminded of the intricate balance that defines Tredecuple systems. Each star, with its unique density, plays a part in the gravitational symphony that holds the system together. These variations not only shape the stars themselves but also influence the broader environment, creating a system that is as complex as it is beautiful. Next, we'll uncover how these systems produce cosmic echoes, where light and sound reverberate through space, revealing even more secrets about these stellar giants. Now, let's turn our attention to a phenomenon that adds another layer of intrigue to Tredecuple star systems' cosmic echoes. These echoes, both in light and sound, are not just remnants of stellar activity. They are powerful tools that help us unravel the mysteries of these complex systems. Imagine a star emitting a burst of light or a shockwave of sound. In the vast emptiness of space, these signals don't just disappear, they bounce, reflect, and reverberate, creating echoes that carry valuable information about the stars and their surroundings. Light echoes occur when a star emits a sudden burst of light, such as during a flare or explosion. This light travels outward, but instead of fading into the void, it encounters dust clouds, gas, or even other stars which reflect it back. These reflections create a delayed echo of the original event, allowing astronomers to study the initial outburst long after it has faded. In Tredecuple systems, where multiple stars and dense interstellar material coexist, light echoes are particularly common. They provide a unique opportunity to observe events that would otherwise be too brief or too distant to study in detail. Sound echoes, on the other hand, are a bit more elusive but equally fascinating. In the plasma-filled environment of a Tredecuple system, sound waves can travel through the hot, ionized gas that surrounds the stars. When a star undergoes a dramatic event, like a collision or a massive explosion, it generates shock waves that ripple through this plasma. These shockwaves can bounce off nearby stars or dense regions of gas, creating sound echoes that reverberate through the system. While we can't hear these echoes directly, sensitive instruments can detect the vibrations they produce, offering insights into the dynamics of the system. What makes these echoes so valuable is the information they carry. Light echoes, for example, can reveal the composition and structure of the interstellar medium, the dust and gas that fill the space between stars. By analyzing the way light is reflected and scattered, scientists can map out the distribution of these materials, gaining a better understanding of how they influence star formation and evolution. Sound echoes, meanwhile, provide clues about the internal dynamics of the system. The way shockwaves propagate and reflect can tell us about the density and temperature of the plasma, as well as the gravitational interactions between stars. In Tredecuple systems, where gravitational forces and stellar interactions are incredibly complex, cosmic echoes serve as a kind of cosmic sonar, helping us see and hear the hidden structures and processes at work. They allow us to piece together the history of these systems, from the violent collisions that shaped them to the subtle interactions that continue to drive their evolution. As we listen to these echoes, we're not just observing the present, we're uncovering the echoes of the past, revealing the stories written in light and sound across the vast expanse of space. Next, we'll dive into the vibrant tapestry of star colors that paint Tredecuple systems, exploring how these hues reveal the diversity and complexity of the stars within them. Now, let's shift our gaze to the dazzling array of colors that define the stars within Tredecuple systems. These systems are not just a chaotic jumble of stars, they are a vibrant cosmic canvas, painted with hues that range from deep reds to brilliant blues. Each color tells a story, revealing the temperature, age, and composition of the stars, and together they create a stunning visual tapestry that helps us understand the complexity of these systems. The colors of stars are determined by their surface temperatures. Hotter stars with temperatures reaching tens of thousands of degrees shine with a brilliant blue or white light. These are often young, massive stars burning through their fuel at an incredible rate. On the other end of the spectrum, cooler stars glow with a reddish hue, indicating lower surface temperatures and often older ages. In Tredecuple systems, where stars of vastly different ages and masses coexist, this color diversity is particularly striking. You might find a blazing blue hypergiant sharing space with a dim red dwarf, creating a stark contrast that highlights the dynamic nature of these systems. But star colors aren't just about aesthetics, they hold critical scientific value. By studying the colors of stars, astronomers can determine their temperatures, which in turn provides clues about their life cycles and evolutionary stages. For example, a blue star's intense heat suggests it's in the prime of its life, while a red star might be nearing the end of its journey, having expanded into a cooler, more luminous phase. In Tredecuple systems, where stars interact and influence each other's evolution, this color diversity becomes a key tool for understanding how these systems form and change over time. The presence of such a wide range of colors also hints at the complex processes at work within Tredecuple systems. Stars of different colors often have different masses and compositions, which can lead to fascinating interactions. For instance, a massive blue star might exert strong gravitational forces on a smaller red companion, pulling material from it and altering its evolution. These interactions can trigger dramatic events such as supernova or the formation of exotic objects like neutron stars or black holes. The colors of the stars, therefore, serve as a visual guide to the intricate dance of gravity and energy that defines these systems. Moreover, the diversity of star colors in Tredecuple systems can help us piece together their history. By analyzing the distribution of colors, scientists can infer the sequence of star formation within the system. A cluster of blue stars might indicate a recent burst of star formation, while a scattering of red stars could point to an older population. This information allows astronomers to reconstruct the timeline of events that shaped the system from its earliest days to its current state. As we marvel at the kaleidoscope of colors in Tredecuple systems, we're reminded of the incredible diversity and complexity of the universe. These systems are not just collections of stars, they are living, evolving entities, each with its own unique story written in light. Next, we'll explore the cosmic tidal forces that shape these systems, uncovering how the gravitational pull of multiple stars creates dramatic and dynamic environments. Now, let's dive into the powerful and often chaotic world of cosmic tidal forces within Tredecuple star systems. These forces, generated by the gravitational pull of multiple stars, create dramatic and dynamic environments that can reshape entire systems. Imagine the gravitational tug of war between stars, each pulling on the others with immense strength, and you'll begin to grasp the sheer intensity of these interactions. In a Tredecuple system, the gravitational forces are not just strong, they're constantly shifting. As stars orbit one another, their gravitational fields interact, creating tidal forces that can stretch and distort nearby objects. Planets, if they exist in such systems, would face extreme challenges. The gravitational pull from multiple stars could tear a planet apart, or at the very least, create wildly unstable conditions. Imagine a world where the ground beneath your feet is constantly being pulled in different directions, with gravity fluctuating so dramatically that the planet's surface could crack or even melt under the strain. But it's not just planets that feel the effects of these tidal forces. Stars themselves can be dramatically altered by the gravitational interactions within a Tredecuple system. For example, a star caught in the gravitational crossfire of multiple companions might experience tidal heating, where its interior is warmed by the constant stretching and compressing caused by the gravitational pulls. This can lead to increased stellar activity, such as flares or eruptions, and even influence the star's evolution over time. The tidal forces in Tredecuple systems can also lead to some truly spectacular cosmic events. When stars pass close to one another, the gravitational interactions can strip material from their surfaces, creating streams of gas and dust that flow between them. These streams can form intricate structures such as bridges or disks, and sometimes even trigger the formation of new stars or planets. In some cases, the tidal forces can be so extreme that they cause stars to merge, resulting in massive explosions or the birth of entirely new stellar objects. One of the most fascinating aspects of these tidal forces is their ability to shape the long-term evolution of Tredecuple systems. Over time, the gravitational interactions can alter the orbits of stars, causing them to spiral closer together or fling one another out of the system entirely. This constant reshuffling of stellar positions ensures that Tredecuple systems are never static. They are always changing, always evolving. As we explore the effects of cosmic tidal forces, we gain a deeper appreciation for the complexity and dynamism of Tredecuple star systems. These forces are not just a side effect of multiple stars sharing space, they are a driving factor in the system's evolution, shaping everything from the smallest planets to the largest stars. Next, we'll turn our attention to the intense magnetic storms that rage within these systems, uncovering how the interplay of magnetic fields can create some of the most extreme conditions in the universe. Now, shifting our gaze to the electrifying realm of star magnetic storms, we uncover another layer of chaos within Tredecuple star systems. These storms are not your average solar flares. They are colossal, high-energy events driven by the complex interplay of magnetic fields generated by multiple stars. In a Tredecuple system where stars are packed closely together, their magnetic fields often collide, twist, and entangle, creating conditions ripe for some of the most intense magnetic activity in the universe. Picture this: a star's magnetic field, already a powerful force, interacts with the fields of its neighboring stars. This interaction can lead to the buildup of immense magnetic energy, which eventually erupts in the form of massive storms. These storms can unleash bursts of radiation, charged particles, and magnetic waves that ripple across the system. The sheer scale of these events is staggering. Some magnetic storms in Tredecuple systems can span entire light years, affecting everything in their path. The consequences of these magnetic storms are profound. For any planets orbiting within these systems, the effects could be catastrophic. Intense radiation from the storms could strip away atmospheres, fry surface conditions, and render planets uninhabitable. Even stars themselves are not immune. The magnetic forces can heat a star's outer layers, triggering violent eruptions or causing its surface to warp and twist. In extreme cases, these storms can even alter a star's rotation or magnetic axis, fundamentally changing its behavior over time. But the drama doesn't stop there. When magnetic fields from multiple stars collide, they can create phenomena known as magnetic reconnection events. These events release enormous amounts of energy, often in the form of X-rays or gamma rays, and can accelerate particles to near light speeds. The result: cosmic fireworks on a scale that defies imagination. These reconnection events can also generate powerful shock waves that ripple through the surrounding space, influencing the formation of new stars or even triggering star formation in nearby gas clouds. One of the most intriguing aspects of these magnetic storms is their role in shaping the long-term evolution of Tredecuple systems. Over time, the constant bombardment of magnetic energy can erode the outer layers of stars, stripping away material and altering their lifespans. In some cases, the storms can even drive stars closer together, increasing the likelihood of collisions or mergers. This relentless magnetic activity ensures that Tredecuple systems remain some of the most dynamic and unpredictable environments in the cosmos. As we delve deeper into the mysteries of star magnetic storms, we begin to see how these events are not just isolated phenomena. They are integral to the life cycle of Tredecuple systems. From reshaping stars to influencing the birth of new celestial objects, these storms are a testament to the raw power and complexity of the universe. Next, we'll explore how Tredecuple systems act as natural particle accelerators, producing high-energy particles that challenge our understanding of physics. Now, let's turn our attention to one of the most fascinating roles Tredecuple star systems play in the cosmos. They act as natural particle accelerators. These systems, with their intricate gravitational and magnetic interactions, are capable of accelerating particles to incredibly high energies, rivaling even the most advanced human-made particle accelerators. But how does this happen in the chaotic environment of a Tredecuple system? The key lies in the intense gravitational and magnetic forces at play. When stars in these systems interact, their gravitational fields can slingshot particles such as protons and electrons to tremendous speeds. At the same time, the tangled magnetic fields generated by multiple stars create powerful electromagnetic environments. These fields can trap charged particles, accelerating them further as they spiral along magnetic field lines. Over time, particles gain so much energy that they are ejected into space at near light speeds, creating streams of high-energy cosmic rays. These cosmic rays are not just random bursts of energy. They carry valuable information about the conditions within Tredecuple systems. By studying them, scientists can gain insights into the magnetic and gravitational dynamics of these complex systems. For instance, the energy levels of these particles can reveal how strong the magnetic fields are or how frequently stars interact gravitationally. In some cases, the particles are so energetic that they can even escape the system entirely, traveling across the galaxy and beyond. But the story doesn't end there. The high-energy particles produced in Tredecuple systems can have far-reaching effects on their surroundings. When these particles collide with gas clouds or other interstellar material, they can trigger secondary processes, such as the formation of gamma rays or even the creation of new particles. This makes Tredecuple systems not just particle accelerators but also cosmic laboratories, where the fundamental laws of physics are tested in extreme conditions. One of the most intriguing aspects of this phenomenon is its potential to challenge our understanding of particle physics. The energies achieved in Tredecuple systems often exceed what we can replicate on Earth, offering a unique opportunity to study high-energy physics in a natural setting. For example, the detection of ultra-high-energy cosmic rays from these systems has sparked debates about their origins and the mechanisms that accelerate them to such extraordinary speeds. As we explore the role of Tredecuple systems as cosmic particle accelerators, we begin to see how these chaotic environments are not just destructive, they are also creative. By accelerating particles to unimaginable energies, these systems contribute to the dynamic and ever-changing nature of the universe. Next, we'll dive into the unique light curves produced by stars in these systems and what they reveal about their behavior and evolution. Now, shifting our gaze to the mesmerizing patterns of light emitted by stars in Tredecuple systems, we uncover another layer of their cosmic complexity. The light curves produced by these stars are not just beautiful, they are packed with scientific treasure. A light curve, for those unfamiliar, is essentially a graph that shows how the brightness of a star changes over time. In simpler star systems, these curves might be relatively predictable, but in Tredecuple systems, they are anything but ordinary. The chaotic dance of 13 stars creates a symphony of light variations. As stars orbit each other, they often eclipse one another from our perspective, causing sudden dips in brightness. These eclipses are just the beginning. The gravitational interactions between stars can distort their shapes, leading to fluctuations in brightness as they stretch and compress. Even more fascinating, the intense magnetic fields in these systems can cause stars to flare unpredictably, adding spikes and dips to the light curve that are unlike anything seen in simpler systems. But why do these light curves matter? For scientists, they are like cosmic fingerprints, revealing the hidden dynamics of Tredecuple systems. By analyzing the patterns in these curves, researchers can determine the sizes, masses, and even the temperatures of the stars involved. They can also uncover details about their orbits, such as how close they are to each other and how fast they are moving. In some cases, the light curves can even hint at the presence of planets or other objects orbiting within the system. One of the most intriguing aspects of these light curves is their ability to reveal starquakes, massive vibrations that ripple across the surfaces of stars. These quakes can cause subtle changes in brightness, providing clues about the internal structure of the stars. Imagine being able to listen to the heartbeat of a star millions of light years away. This is the kind of insight light curves can offer. Beyond their scientific value, these light curves also remind us of the sheer dynamism of Tredecuple systems. They are not static or unchanging. They are alive with activity, constantly shifting and evolving. Each flicker and flare tells a story of gravitational tugs, magnetic storms, and cosmic collisions. As we continue to study these light curves, we gain not only a deeper understanding of Tredecuple systems, but also a greater appreciation for the intricate beauty of the universe. Next, we'll explore how the precise movements of stars in these systems can act as cosmic timekeepers, offering us a unique way to measure the passage of time on a universal scale. Now, let's turn our attention to a fascinating aspect of Tredecuple star systems, their role as cosmic timekeepers. The precise movements of stars within these systems offer a unique way to measure time on a universal scale, providing insights that go far beyond our everyday understanding of clocks and calendars. In Tredecuple systems, the gravitational interactions between 13 stars create highly predictable orbital patterns. These patterns, though complex, follow the laws of physics with remarkable precision. By tracking the positions and movements of these stars over time, astronomers can use them as natural clocks. Each orbit, each eclipse, and each gravitational tug acts like a tick of a cosmic second hand, marking the passage of time in ways that are both accurate and awe-inspiring. One of the most remarkable applications of this phenomenon is in measuring the age of the universe itself. By observing how stars in Tredecuple systems move and interact, scientists can calculate the time it takes for these systems to complete their intricate dances. These measurements can then be compared to other cosmic events, such as the expansion of the universe or the life cycles of stars, to create a more comprehensive timeline of cosmic history. But the precision of these cosmic timekeepers doesn't stop there. The gravitational waves produced by the movements of stars in Tredecuple systems also carry information about time. As these waves ripple through space, they create subtle distortions that can be detected by advanced instruments. These distortions act like cosmic echoes, allowing scientists to trace the movements of stars back in time and gain a deeper understanding of how these systems have evolved over billions of years. What makes this even more extraordinary is the sheer scale of time involved. While we measure our lives in years, decades, or centuries, Tredecuple systems operate on timescales that span millions or even billions of years. By studying them, we gain a perspective on time that is both humbling and enlightening. It's a reminder that the universe operates on a timeline far beyond human comprehension, yet it is governed by the same fundamental principles that shape our everyday lives. As we continue to explore these cosmic timekeepers, we not only refine our understanding of time itself, but also uncover new clues about the origins and future of the universe. Next, we'll delve into the massive magnetic loops that form between stars in Tredecuple systems and the extraordinary effects they have on their surroundings. Now, let's shift our gaze to another mesmerizing feature of Tredecuple star systems, the massive magnetic loops that form between stars. These loops are not just visually stunning, they play a crucial role in shaping the dynamics of these complex systems. Imagine a cosmic web of magnetic fields stretching across vast distances, connecting stars in ways that defy our everyday understanding of magnetism. In Tredecuple systems, the intense magnetic fields generated by each star interact with one another, creating enormous loops that arc through space. These loops are formed when the magnetic fields of two or more stars become entangled, often due to their close proximity and rapid movements. The result is a network of magnetic pathways that can stretch for light years, weaving a tapestry of energy that influences everything around it. One of the most striking effects of these magnetic loops is their ability to channel charged particles, such as electrons and protons, across vast distances. This creates streams of high-energy plasma that flow along the loops, often leading to spectacular phenomena like solar flares or coronal mass ejections. These events can release immense amounts of energy, illuminating the surrounding space with bursts of light and radiation. But the influence of these magnetic loops doesn't stop there. They also play a key role in regulating the temperatures of stars within the system. By transferring heat and energy between stars, the loops help maintain a delicate balance that prevents some stars from overheating while ensuring others don't cool down too much. This thermal regulation is essential for the stability of the system as a whole, preventing catastrophic events like premature supernova. Another fascinating aspect of these magnetic loops is their ability to act as cosmic accelerators. The intense magnetic fields can accelerate particles to near light speeds, creating jets of energy that shoot out from the stars. These jets can travel vast distances, sometimes even escaping the gravitational pull of the system and venturing into interstellar space. The presence of these magnetic loops also has implications for any planets or other celestial bodies within the system. The intense radiation and particle streams generated by the loops can strip away atmospheres or bombard surfaces with high-energy particles, making it challenging for life to exist in such environments. Yet, they also create opportunities for unique chemical reactions, potentially leading to the formation of exotic materials or even new forms of matter. As we continue to study these magnetic loops, we uncover more about the intricate interplay of forces that govern Tredecuple star systems. They remind us that the universe is not just a collection of isolated objects, but a dynamic, interconnected web of energy and matter. Next, we'll explore how Tredecuple systems can act as cosmic echo chambers, amplifying and reflecting the events that occur within them. Now, let's turn our attention to another extraordinary feature of Tredecuple star systems, their ability to act as cosmic echo chambers. Picture this, a vast, interconnected network of stars, each one sending out ripples of energy and sound that bounce and reverberate through the system. These echoes aren't just random noise, they carry valuable information about the events that created them, offering astronomers a unique way to study the inner workings of these complex systems. In Tredecuple systems, the sheer number of stars and their close gravitational interactions create an environment where sound waves and energy pulses can travel great distances without dissipating. When a star undergoes a dramatic event, such as a massive flare or a collision, the resulting shock waves ripple through the surrounding space. These waves can bounce off other stars, gas clouds, or even the magnetic loops we discussed earlier, creating echoes that linger long after the initial event. These cosmic echoes are not just fascinating to observe, they serve as a powerful tool for scientists. By analyzing the patterns and timing of these echoes, researchers can piece together the sequence of events that triggered them. For example, if a star in a Tredecuple system explodes in a supernova, the echoes of that explosion can reveal details about the star's structure, the forces at play, and even the composition of the surrounding space. It's like listening to the universe's own version of a recording, replaying the moments that shaped it, but the echoes don't just stop at sound waves. Light and radiation can also bounce around within these systems, creating visual echoes that astronomers can detect. Imagine a burst of light from a star explosion traveling through the system, reflecting off dust clouds or other stars and arriving at our telescopes at different times. These delayed signals provide a kind of cosmic time-lapse, allowing us to see the same event from multiple angles and moments in time. The concept of Tredecuple systems as echo chambers also opens up intriguing possibilities for studying the universe's most energetic events. For instance, the collision of two neutron stars or the formation of a black hole can send out gravitational waves that echo through the system. These waves, though invisible, carry information about the objects that created them, offering a new way to explore the mysteries of gravity and spacetime. What makes these echo chambers even more remarkable is their ability to amplify certain signals. Just as sound can be amplified in a physical echo chamber, the energy and waves within a Tredecuple system can be magnified as they bounce between stars. This amplification can make faint signals detectable, allowing astronomers to observe events that would otherwise be too distant or weak to study. As we continue to explore Tredecuple star systems, the echoes they produce will undoubtedly reveal even more about the universe's most dramatic events. They remind us that the cosmos is not just a silent void, but a vibrant, resonant space filled with the echoes of its own history. Next, we'll dive into the fascinating world of plasma jets emitted by stars in these systems and the incredible impact they have on the surrounding space. Now, shifting our gaze to another awe-inspiring phenomenon, let's explore the dramatic plasma jets emitted by stars within Tredecuple systems. These jets are not just spectacular to observe, they play a crucial role in shaping the environment around them. Picture a star unleashing a torrent of superheated plasma, a stream of charged particles racing through space at incredible speeds. These jets can stretch for light years, carving their way through the cosmic landscape and leaving a lasting impact on everything in their path. In Tredecuple star systems, the presence of multiple stars creates a dynamic environment where plasma jets can interact in fascinating ways. When one star emits a jet, it doesn't just travel unimpeded. Instead, it can collide with the magnetic fields, gas clouds, or even the jets of neighboring stars. These interactions can lead to spectacular displays of energy, such as shock waves, bursts of radiation, or even the formation of new structures within the system. The sheer complexity of these interactions makes Tredecuple systems a treasure trove for astronomers studying plasma dynamics. One of the most intriguing aspects of these plasma jets is their ability to influence star formation. As the jets travel through space, they can compress nearby gas clouds, triggering the birth of new stars. This process, known as triggered star formation, is particularly significant in Tredecuple systems, where the density of stars and gas is already high. The jets act like cosmic sculptors, shaping the system's structure and contributing to its ongoing evolution. But the impact of plasma jets isn't limited to star formation. They also play a role in the distribution of matter and energy throughout the system. When a jet collides with a gas cloud or another star's magnetic field, it can transfer energy and momentum, heating the surrounding material and altering its trajectory. This process can create regions of intense radiation, which astronomers can observe to learn more about the conditions within the system. In some cases, these interactions can even lead to the ejection of material from the system entirely, sending it out into the wider universe. The study of plasma jets in Tredecuple systems also provides valuable insights into the behavior of matter under extreme conditions. The temperatures and pressures within these jets are unlike anything we can replicate on Earth, making them natural laboratories for understanding plasma physics. By observing how these jets behave and interact, scientists can test theories about magnetic fields, particle acceleration, and energy transfer in ways that would be impossible in a laboratory setting. As we continue to unravel the mysteries of Tredecuple star systems, the study of plasma jets will undoubtedly remain a key area of interest. These powerful streams of energy not only shape the systems they inhabit, but also offer a window into the fundamental processes that govern the universe. Next, we'll delve into the phenomenon of magnetic reconnection in these systems and how it drives some of the most energetic events in the cosmos. Now, let's turn our attention to one of the most energetic and mysterious processes in Tredecuple star systems, cosmic magnetic reconnection. This phenomenon occurs when the magnetic fields of multiple stars interact, break apart, and then reconnect in new configurations. Imagine two powerful magnets snapping together, releasing a burst of energy, except here, we're talking about magnetic fields on a cosmic scale, capable of unleashing staggering amounts of power. In Tredecuple systems, where multiple stars are packed relatively close together, magnetic reconnection is a common and dramatic event. Each star generates its own magnetic field, and when these fields come into contact, they can twist, tangle, and eventually snap into new alignments. This process releases vast amounts of energy, often in the form of intense bursts of radiation, plasma jets, or even explosive flares. These events can heat the surrounding material to extreme temperatures, creating regions of intense activity that astronomers can observe from great distances. One of the most fascinating aspects of magnetic reconnection is its role in accelerating particles to near light speeds. When the magnetic fields reconnect, they create powerful electric fields that can propel charged particles outward at incredible velocities. These particles, often electrons and protons, can then collide with other matter in the system, producing high-energy radiation such as X-rays or gamma rays. This makes Tredecuple systems natural particle accelerators, offering scientists a unique opportunity to study how particles behave under extreme conditions. The effects of magnetic reconnection aren't limited to the stars themselves. The energy released during these events can ripple through the entire system, influencing the orbits of planets, triggering star formation, or even ejecting material into interstellar space. In some cases, the reconnection process can create shock waves that travel through the surrounding gas clouds, compressing them and potentially sparking the birth of new stars. This interplay between magnetic fields and matter is a key driver of the dynamic and ever-changing nature of Tredecuple systems. Studying magnetic reconnection in these systems also provides valuable insights into broader astrophysical processes. Similar events occur in the Sun's atmosphere, in the magnetospheres of planets, and even in the jets of black holes. By observing how magnetic reconnection unfolds in Tredecuple systems, scientists can refine their understanding of this universal phenomenon and apply it to other areas of astrophysics. As we continue to explore the complexities of Tredecuple star systems, magnetic reconnection stands out as a powerful force shaping their evolution. From accelerating particles to triggering star formation, this process is a testament to the intricate interplay of forces at work in the cosmos. Next, we'll examine another striking feature of these systems, the frequent surface explosions that light up their stars like cosmic fireworks. Now, let's shift our focus to one of the most visually stunning phenomena in Tredecuple star systems, the frequent surface explosions that light up these stars like cosmic fireworks. These explosions, often referred to as stellar flares or eruptions, are not just spectacular to observe. They also reveal critical details about the behavior of stars in such complex systems. In Tredecuple systems, where multiple stars orbit in close proximity, the gravitational and magnetic interactions between them create an environment ripe for instability. Stars in these systems are often subjected to intense tidal forces and magnetic stresses, which can cause their surfaces to become highly volatile. When the pressure builds up, it can lead to sudden and violent releases of energy in the form of surface explosions. These events can be thousands or even millions of times more powerful than the solar flares we observe on our own sun. The primary cause of these explosions lies in the twisting and snapping of magnetic fields. As stars in a Tredecuple system interact, their magnetic fields can become tangled and strained. When these fields eventually snap back into place, they release enormous amounts of energy, heating the star's outer layers to extreme temperatures. This sudden heating causes the star's surface to erupt, sending massive bursts of radiation, charged particles, and plasma into space. These eruptions can last anywhere from a few minutes to several hours, illuminating the surrounding area with intense light and energy. One of the most intriguing aspects of these surface explosions is their impact on the broader system. The energy released during these events can ionize nearby gas clouds, trigger shock waves, and even influence the orbits of other stars or planets. In some cases, the explosions can strip away a star's outer layers, leaving behind a denser core or even altering its evolutionary path. This makes surface explosions not just a dramatic spectacle, but also a key driver of the dynamic processes within Tredecuple systems. Astronomers have also observed that these explosions can produce a wide range of electromagnetic radiation, from visible light to X-rays and gamma rays. This makes them valuable tools for studying the physical conditions within Tredecuple systems. By analyzing the light and radiation emitted during these events, scientists can gain insights into the temperatures, densities, and magnetic properties of the stars involved. As we continue to explore the mysteries of Tredecuple star systems, these surface explosions serve as a vivid reminder of the immense forces at play. They highlight the delicate balance between stability and chaos in these cosmic environments, offering a glimpse into the life cycles of stars and the intricate dance of gravity and magnetism that shapes their existence. Next, we'll delve into another fascinating feature of these systems: how their intense gravity bends light, creating mesmerizing visual effects that challenge our understanding of the universe. Now, let's turn our attention to one of the most mind-bending phenomena in Tredecuple star systems: the way their immense gravity warps the very fabric of space and time, bending light in ways that defy our everyday understanding of physics. This cosmic light bending, also known as gravitational lensing, is not just a fascinating visual spectacle, it's a powerful tool that helps astronomers unravel the secrets of these complex systems. In Tredecuple systems, the combined gravitational pull of multiple stars creates an incredibly strong gravitational field. When light from a distant star or galaxy passes near this field, it doesn't travel in a straight line as we might expect. Instead, the intense gravity bends the light's path, much like a magnifying glass bends sunlight. This bending can create a variety of stunning visual effects, from distorted images of distant objects to multiple images of the same star appearing in different positions in the sky. One of the most striking examples of this phenomenon is the formation of Einstein rings. These are circular or nearly circular rings of light that form when the light from a distant object is bent around a massive object, like a Tredecuple star system, in such a way that it appears to surround it. These rings are not only beautiful to observe, but also provide valuable information about the mass and distribution of the stars within the system. By studying the size and shape of these rings, astronomers can estimate the total mass of the system and even detect the presence of hidden objects such as black holes or dark matter. Another intriguing effect of cosmic light bending is the creation of multiple images of a single object. When light from a distant star or galaxy passes through the gravitational field of a Tredecuple system, it can be split into multiple paths, each bending at a slightly different angle. This results in the same object appearing in multiple places in the sky, sometimes with slight variations in brightness or color. These multiple images can act as cosmic magnifying glasses, amplifying the light from distant objects and allowing astronomers to study them in greater detail than would otherwise be possible. The bending of light in Tredecuple systems also has practical implications for our understanding of the universe. By observing how light is distorted as it passes through these systems, scientists can test the predictions of Einstein's theory of general relativity with incredible precision. These observations have confirmed that gravity does indeed warp space and time, just as Einstein predicted, and have provided new insights into the nature of gravity itself. As we continue to explore the mysteries of Tredecuple star systems, the phenomenon of cosmic light bending serves as a vivid reminder of the profound influence gravity has on the universe. It challenges our perceptions of reality and offers a glimpse into the intricate interplay of forces that shape the cosmos. Next, we'll dive into another captivating aspect of these systems: what happens when the magnetic fields of multiple stars collide, creating explosive interactions that light up the universe. Now, let's shift our focus to another electrifying phenomenon in Tredecuple star systems: the collision of magnetic fields. When multiple stars with their own powerful magnetic fields come into close proximity, the results are nothing short of spectacular. These interactions can unleash bursts of energy, trigger massive stellar flares, and even reshape the entire system's dynamics. In a Tredecuple system, each star generates its own magnetic field, which extends far into space. When these fields overlap or collide, they don't just quietly coexist, they interact in dramatic ways. Imagine two powerful magnets being pushed together. The forces at play are intense and unpredictable. In the case of stars, these magnetic collisions can lead to a process called magnetic reconnection. This occurs when the magnetic field lines break and reconnect, releasing enormous amounts of energy in the form of heat, light, and charged particles. One of the most visible effects of these collisions is the creation of massive stellar flares. These flares can be millions of times more powerful than anything our sun produces, lighting up the surrounding space with bursts of radiation. For astronomers, these flares are like cosmic fireworks, offering a glimpse into the chaotic energy of Tredecuple systems. But they're not just a visual spectacle, they also provide clues about the strength and structure of the star's magnetic fields. Another consequence of magnetic field collisions is the acceleration of charged particles to incredibly high speeds. These particles, often electrons and protons, can spiral along the magnetic field lines, gaining energy as they go. When they're eventually released, they can create intense beams of radiation, such as X-rays or gamma rays. These beams can travel vast distances, impacting nearby planets or even other star systems. In some cases, they might even influence the formation of new stars or planets by heating up surrounding gas and dust. The collision of magnetic fields can also have a profound impact on the stars themselves. The forces involved can distort the star's surfaces, creating massive sunspots or triggering eruptions of plasma. Over time, these interactions can even alter the star's rotation rates or magnetic field strength, leading to long-term changes in the system's structure. For example, a star with a weakened magnetic field might become more susceptible to stellar winds, losing mass at a faster rate than its neighbors. What makes these magnetic collisions even more fascinating is their role in shaping the broader environment of Tredecuple systems. The energy released during these events can heat up the surrounding space, creating regions of intense radiation that affect everything from planetary atmospheres to the formation of cosmic dust clouds. In some cases, these interactions might even trigger the birth of new stars, as the energy from magnetic reconnection compresses nearby gas and dust. As we explore the magnetic chaos of Tredecuple systems, it's clear that these collisions are more than just cosmic accidents. They're fundamental processes that drive the evolution of these complex systems. They remind us that even in the vastness of space, the forces at play are deeply interconnected, shaping the universe in ways we're only beginning to understand. Next, we'll delve into another explosive aspect of these systems: the massive energy bursts that light up the cosmos and challenge our understanding of stellar physics. Now, let's turn our attention to one of the most awe-inspiring phenomena in Tredecuple star systems: cosmic energy bursts. These bursts are not just fleeting flashes of light, they are colossal releases of energy that can outshine entire galaxies for brief moments. But what causes these explosive events, and what do they tell us about the inner workings of these complex systems? Cosmic energy bursts in Tredecuple systems often originate from the intense gravitational and magnetic interactions between the stars. When multiple stars orbit each other in such close proximity, their gravitational fields can pull and twist on one another, creating immense tension. This tension builds up until it's released in a sudden, violent burst of energy. Think of it like a rubber band being stretched to its limit. Once it snaps, the energy is unleashed in an instant. One of the primary sources of these bursts is the collision of stars or their remnants. In a Tredecuple system, the chaotic orbits can sometimes lead to stars crashing into one another. When this happens, the resulting explosion releases an enormous amount of energy, often in the form of gamma rays or X-rays. These collisions are so powerful that they can be detected across vast distances, providing astronomers with valuable data about the system's dynamics. Another source of cosmic energy bursts is the interaction between stars and black holes. In some Tredecuple systems, black holes lurk among the stars, their immense gravity pulling on nearby matter. When a star gets too close to a black hole, it can be torn apart in a process called tidal disruption. As the star's material spirals into the black hole, it heats up and emits a tremendous burst of energy. These events are not only spectacular to observe, but also offer insights into the behavior of black holes in multi-star systems. Magnetic reconnection, which we discussed earlier, also plays a significant role in generating energy bursts. When the magnetic fields of multiple stars collide and reconnect, they release vast amounts of energy in the form of heat, light, and charged particles. This process can trigger sudden flares or jets of radiation that shoot out into space, illuminating the surrounding area with intense bursts of light. The energy released during these events doesn't just vanish into the void, it has a profound impact on the surrounding environment. These bursts can heat up nearby gas and dust, triggering the formation of new stars or even entire planetary systems. They can also strip away the atmospheres of existing planets, altering their climates and potentially making them uninhabitable. In some cases, the energy from these bursts can travel across interstellar space, influencing other star systems far beyond their origin. What makes these cosmic energy bursts truly remarkable is their ability to challenge our understanding of stellar physics. The sheer scale of energy involved forces scientists to rethink how stars and black holes interact in such crowded systems. Each burst provides a unique opportunity to study the extreme conditions that exist in Tredecuple systems, shedding light on the processes that shape the universe. As we continue to explore these explosive phenomena, one thing becomes clear. Tredecuple star systems are not just static collections of stars, they are dynamic, ever-changing environments where the forces of gravity, magnetism, and energy collide in spectacular ways. Next, we'll take a closer look at the ultimate fate of these systems and what their evolution tells us about the life cycles of stars. Now, as we peer into the cosmic horizon, let's ponder the ultimate destiny of Tredecuple star systems. These intricate stellar families, with their chaotic orbits and explosive interactions, are not eternal. Like all things in the universe, they too are subject to the relentless march of time and the forces that shape their existence. So, what lies ahead for these extraordinary systems? Over millions or even billions of years, the stars within Tredecuple systems will continue to evolve, each following its own unique path. Some stars will exhaust their nuclear fuel, swelling into red giants before shedding their outer layers and collapsing into dense remnants like white dwarfs, neutron stars, or even black holes. Others, particularly the most massive stars, may end their lives in spectacular supernovae, scattering their material across the cosmos and seeding the surrounding space with the building blocks for future stars and planets. As these transformations occur, the gravitational dynamics of the system will shift dramatically. Stars that once danced in delicate balance may be flung out of the system entirely, ejected by the gravitational slingshot effect of their neighbors. Others may spiral closer together, leading to more collisions or the formation of tighter binary or triple star pairs. Over time, the system could fragment into smaller, more stable groupings, or it might collapse into a single, massive black hole surrounded by a swirling disk of debris. One intriguing possibility is that some Tredecuple systems could give rise to hypermassive black holes. As stars collide and merge, their combined mass could create a gravitational behemoth capable of devouring nearby stars and gas. These black holes could grow to unimaginable sizes, becoming some of the most massive objects in the universe. Their immense gravity would warp space-time itself, creating regions where the laws of physics as we know them break down. But the story doesn't end there. Even as individual stars fade or collide, the legacy of Tredecuple systems lives on. The heavy elements forged in their cores and scattered by their explosive deaths become the raw materials for new stars, planets, and perhaps even life. In this way, Tredecuple systems contribute to the ongoing cycle of cosmic creation and destruction, playing a vital role in the evolution of galaxies. Yet, the ultimate fate of these systems remains shrouded in mystery. Will they dissolve into the void, their stars scattered across the galaxy, or will they leave behind a lasting imprint, such as a supermassive black hole or a cluster of exotic stellar remnants? The answers to these questions lie in the distant future, far beyond the reach of our current observations. What we do know is that Tredecuple star systems are a testament to the dynamic and ever-changing nature of the universe. They remind us that even the most stable-seeming structures are in a constant state of flux, shaped by the interplay of gravity, energy, and time. As we continue to study these systems, we gain not only a deeper understanding of their evolution, but also a greater appreciation for the intricate tapestry of the cosmos. And with that, we've reached the end of our journey through 50 strange and fascinating discoveries about Tredecuple star systems. From their chaotic orbits to their explosive energy bursts, these systems have challenged our understanding of the universe and inspired us to look deeper into the mysteries of space. If you've enjoyed this cosmic exploration, don't forget to like, subscribe, and hit the notification bell for more mind-bending journeys into the wonders of the universe. Until next time, keep looking up. The stars have so much more to reveal. As we wrap up this cosmic journey, let's take a moment to reflect on the incredible discoveries we've explored about Tredecuple star systems. These complex stellar families have revealed a universe far more dynamic and mysterious than we ever imagined. From their chaotic orbits and rare star types to the extreme gravitational forces and mysterious radio signals, each discovery has deepened our understanding of the cosmos. These systems challenge our assumptions, showing us that the universe is a place of constant change, where stars collide, black holes form, and new worlds are born from the ashes of the old. Tredecuple star systems are more than just astronomical curiosities. They are windows into the fundamental processes that shape galaxies and drive the evolution of the universe itself. They remind us that even the most stable-seeming structures are governed by forces beyond our comprehension, and that every star, every planet, and every particle of dust plays a role in the grand cosmic story. By studying these systems, we not only uncover the secrets of their formation and fate, but also gain insights into the origins of the elements that make up our world and even our own existence. As we close this chapter, I want to thank you for joining me on this journey through the wonders of Tredecuple star systems. If you've enjoyed unraveling these cosmic mysteries, don't forget to share your thoughts in the comments below. What discovery fascinated you the most? What questions do you still have about these incredible systems? Let's keep the conversation going. And if you're eager for more mind-expanding explorations of the universe, make sure to hit that subscribe button and turn on notifications. There's so much more to discover, and I can't wait to share it with you. Until next time, keep looking up. The stars are waiting to tell their stories.